Hi, and welcome to Managing Cloud-Native Applications with Kubernetes. My name is Marek Czernek. I'm a senior curriculum developer at Red Hat, one of the developers for this course, and I'll be the instructor throughout this course. So this is the second course in this specialization, and like all of our courses, this course comes with a very handy PDF. So I would definitely encourage you to grab that PDF, take a look at that PDF, read through that PDF. Do not rely only on my videos, but read through that PDF as well, because it might contain different information. And what I want to do right now is go through that PDF and take a look at what this course is going to be all about and what we need to know before we actually start the content of this course. So let's grab the handy PDF and let's take a look. So throughout this course, we are going to be starting by taking a look at what it means for an application to be managed, right? And what benefits does it provide if we have an application that actually has some kind of a manager, such as deployment within Kubernetes. Then we are going to take a look at networking within Kubernetes, both exposing an application for internally, all right, internal access, as well as so within Kubernetes, as well as for ingress. So how do we enable external access outside of the Kubernetes cluster to our resource? Then what we are going to do is take a look at how we can limit resource usage for our resources. We are going to prove that our application is ready to serve requests and that it is live, right? And we are going to decouple the configuration from our source code, right? From our application. And last but definitely not least, we are going to take a look at some cloud deployment strategies and how do we actually update our application on Kubernetes, right? What are some of the strategies that we can employ to update our application? So this is the second course of our specialization, and it has some prerequisite setup. I would strongly encourage you to go through our first course for the setup of our Kubernetes cluster and everything around it. If you have done so, then you have your setup done, and that's excellent. If you haven't, and you don't want to go through the first course, then that's perfectly fine. We provide the appendices over here, right? We provide appendices A and B, where we provide some information on what is some of the configuration that we expect through this course. And I will not go through the step-by-step of how to do that, right? So if you are interested in step-by-step and me following the instructions, take a look at our first course in this specialization. If all you want is just to set up the environment so that you can follow along with this course, then we provide the appendices. So what do we need to know before we actually start? Well, this classroom is bring your own developer workstation, and we support multiple workstation systems, multiple operating systems. Namely, we support Linux, we support Windows, as well as Mac OS. So take a look at the recommended minimum and recommended system requirements and make sure that you fulfill at the very least the minimum requirements so that you can go through the contents of this course. This course requires some programs to be installed, such as the kubectl, which we will definitely use a lot. Minikube is optional. This is the Kubernetes distribution that I'm going to be using throughout the course. But it is optional. You can, of course, use the cloud version or cloud distribution of Kubernetes, which is the OpenShift sandbox environment that is completely free. And again, check the appendix or the first course for some setup information. And then Git is helpful if you want to clone the DO100 X apps repository, right? So we have some systems support consideration. And the one thing that I would like to mention is the default prompt, right? So let me switch to my terminal application and let me take a look at what prompt is. So throughout this course, we are going to have a lot of guided exercises, and I would definitely encourage you to go through the guided exercises with me. And one thing that might surprise you is that within the guided exercises, a lot of the commands start with a prompt, and the prompt is something like this, right? So this is my prompt, and the prompt contains my username, my host name, right? Then we have our location on the system. This is all enclosed in brackets, and then I have the signifier that this is a non-root terminal shell, right? So this is the $sign. So this is the terminal prompt that is on Linux. This prompt might look different, for example, even on macOS, but will definitely look different on Windows. So on Windows, the supported terminal application is PowerShell, right? And in PowerShell, the prompt will look definitely different. The PowerShell starts with the letters PS, which stands for PowerShell, right? And then we have our location, and then we have our greater than symbol, right? And then we can type our commands. So what I wanted to say is don't worry if the prompt looks different. Essentially, our guided exercises are designed such that the commands after the prompt should work for all of the supported systems. And if they do not, for example, if the command is different on Windows, then we will tell you so, right? One thing to keep in mind is that the only supported terminal application for Windows is PowerShell, okay? Do not try to run the commands in anything but PowerShell on Windows, of course. So the next thing that I wanted to talk about is executing long commands. And so throughout the guided exercises, what we do for stylistic reasons is we take our commands, and when we have long commands, we break them by using this / character, right? So whenever we have long commands, we use this / character and we break the long commands into multiple lines, right? And so this will work on a Linux or macOS system. However, on the Windows system, we have to use the backtick character, right? So if we have a long command, we have to use backtick to break long command, or alternatively, we can type it in one. We can type it on one line, right? And we don't have to break long commands. So let's take a look at how that actually works in practice. So for example, on my left-hand side, I have my my bash terminal, my terminal that runs the bash shell. And so what I can do is I can type long command, right? I can type echo and break the long command with the /, then type hello and world. And so each new line contains a /, except for the last new line, which simply executed the command, right? And so this is equivalent to simply typing echo hello world, right? And so the output of these two commands is identical. However, in the PowerShell shell, right? What we have to do is we can't use this backslash when we break on multiple lines, right? We have to use the backtick character. And so backtick is not a quote, right? Is not a single quote, is not a double quote. It is a backtick character. So this is a different character, right? And so we can actually type echo, right? And then backtick, and then hello, backtick world, right? And so this is absolutely equivalent to typing out the command on one line. So it is up to you. It is up to you what you want to follow, right, within the guided exercises. Throughout the guided exercises, I will simply type out the commands in one line, right? Just be aware that if you are using Windows, you can't use the backslash character. You have to use the backtick character. So that was enough for the introduction to the course. Let's get actually started with our chapter 1. So welcome to the first video of this course. And in this video, we are going to be talking about deploying managed applications, right? So in the previous course, in the part A of this course, and in the first course of the specialization, we left off with deploying some workloads to our cluster, right? And so what we did was we had our application, right? This is our containerized application. And because it's a container, right, we can isolate it from the rest of our environment. Kubernetes, however, as we know, does not work with containers directly. Kubernetes works with an abstraction, right, of on top of a container, which we call pods, right? So we have a pod which can have one or multiple containers in it, and we spawned our application in Kubernetes, right? Which was a single container pod. And so what happens to this pod, for example, when the application crashes inside? So this is a question, right? What happens when the application has a bug and exits with a non-zero code? Well, this is a single container pod, right? The application crashes. That means the whole pod crashes, right? So this is not ideal from multiple perspectives, right? We would like this to be a bit more automated. We would like to get more out of Kubernetes, right? If you remember in the beginning of part A of this course, right, we talked about this virtualized and bare metal deployments. Where when we have our application on something like a bare metal machine and it crashes, we have to restart it manually, for example, unless we have some custom automation that we create, right? Or use some third-party automation. Well, now we are deploying on Kubernetes, right? And it would be nice to have some kind of a watcher, right? Or a watch loop. So some kind of a concept, some kind of an abstraction that actually watches the pod, right? And if it happens that the pod dies, right, we would like this watcher, this manager, to spawn a new pod, right, with our application. So we can actually create this application inside of a second pod, right? And this would be a second pod, right? And the watcher would continue manage this new pod. Well, it turns out that there is a concept of this watcher in Kubernetes, and this is called a deployment. So a deployment is a Kubernetes resource which defines an application, right? Defines a set of pods which it manages, right? That's why we talk about managed applications in this video, right? Managed by what or managed by whom? Well, managed by Kubernetes, right? And the manager, the watcher within Kubernetes can be, for example, a deployment, right? This is one of the manager within Kubernetes, right? So the question is, what do we want from managers from Kubernetes, right? Kubernetes comes with a number of managers, right? A number of watch loops that it implements. What do we want from Kubernetes ideally? What we definitely want, right, is to declare what is the status of the application, right? So we want to declare what the application should look like. And then we want Kubernetes to go off and simply make it happen, right? So I, as a developer, don't really care how Kubernetes does things, right? I don't want to be forced to create my custom code, right? In order to spawn a new application. I don't want to be forced to create, let's say, Docker commands or Podman commands or cryo commands in order for Kubernetes to spawn my containerized applications, right? What I want to say to Kubernetes is, this is what I want my application to look like, right? Make it happen, and Kubernetes will do so. And this is what we call the declarative approach, right? And this is in contrast with the imperative approach, where you program exactly what should happen in what steps, right? And then the platform would execute it, right? So in Kubernetes, we use the declarative approach, where we specify a manifest file, right? We specify the status of our application, and Kubernetes should manage that, right? So what do we specify? We specify a number of things. For example, the container images, right? We have done that even in our in the previous part 1 of this course, right? In the first course in this specialization, we can specify number of replicas. How many pods do we want to spawn, right? For example, how many pods should our deployment manage, right? It is a manager. If it can spawn 1 pod, why couldn't it spawn 100, right? And the strategy for updating, and we'll take a look at that, right? What can Kubernetes and its manager and watch loops do for us, right? Well, we've taken a look at the automatic restart, right? And we have something like the concept of the deployment, which, for example, when the pod crashes and the pod is a managed pod by a deployment, the deployment can realize, right? Can interrogate the pod, discover that the pod is no longer in the running state, and therefore the state, the reality, does not conform to the declared state, right? Well, what does that mean? Well, we have to create a new pod. And so Kubernetes creates a new pod, which means restarting our application, right? Without intervention from the developer. Excellent, right? We can have automatic rollout, right? When I update my image, container image, right? Kubernetes can automatically roll out this update without any connectivity loss to the application, right? And we'll be taking a look at that as well. Automatic scaling. So this is a different manager application, or different manager within Kubernetes, right? Which basically takes a look at the consumption of resources across pods, right? And if the pods consume more resources than the developer specified, then we can automatically spawn new new pods, or vice versa, right? If the pods consume less resources, then we can decommission some pods. And automatic deployment, we have seen that you specify you want a pod, Kubernetes deploys that pod for you, right? So this is what we mean by managing containers. Who is managing the containers? Well, Kubernetes is for us, right? And then ideally, you would use some kind of a manager within Kubernetes, like the deployment resource, so that you get some benefits, for example, automatic restart, right? And this depends on the particular manager resource within Kubernetes that you want to use. So we know about a deployment as a manager program or manager loop within Kubernetes, right? A deployment manages or watches our pods. How do we actually create a manager or a deployment within Kubernetes? Well, of course, we can use our kubectl utility, right? And we can use the create command, and we have actually seen this command before, right? So the create command takes a resource, a named resource, right? So what are we creating? Well, we are creating a deployment. Then we want to take a deployment name, right? We name our deployment somehow. And then at the very least, we need an image. And then we can specify some parameters such as the number of replicas, right? We can also get a deployment, right? Just like we got, we issued kubectl get, right? And we use that for pods. Well, we can use kubectl get command for the deployment resource as well, right? And so if we issue kubectl get deployment, then following the deployment name, we get the deployment name, right? Kubernetes responds with the deployment status. And if we specify the output YAML, right, we get a lot of, we get the full YAML representation of the resource, right? We essentially get the status, the full manifest of the resource in the YAML format. So this is quite helpful, and it's quite helpful to understand the YAML resource, right? So let's take a look. Let's try to understand what the YAML resource means. So each resource within Kubernetes has some kind of a kind, right? And this is how you know what type of resource it is. So kind starts with capital letter, right? Starts with capital letter, and this is a deployment resource, and so that's why we have a deployment. Then we have some kind of metadata, right? And the metadata contains the name of the resource. So this resource name, this deployment's name is versioned -hello, right? And then we have our labels. And labels in Kubernetes very important, right? Labels are simply key value pairs, right? So app is the key and versioned hello is the value, right? And then we have the spec. This is the specification, right? And the specification defines the specification for the deployment. So we define that we have 3 replicas. This means the deployment will spawn 3 container images, right? Or 3 pods. 3 pods, each of them will have 1 container image. And we can define the strategy, right? And the strategy we'll take a look at later. And finally, we have our template. And within the template, we have another spec, right? And this is where we specify the specification of the pods that we want to spawn, right? And so right now, because this is the output of kubectl get, right? we get actually the spawned containers. So we have the containers, right? This is an array. So this means that we can have multiple containers, and this particular container uses this image, right? Red Hat Training versioned hello, and has this particular name. So this is the name of the container within a pod, not the pod itself, right? So the deployment manages the pods, therefore it manages the names of the pod. The names of the containers we can set, but they are not that important if you use single container pods, right? And finally, we have our status. So this is the status of the deployment as it is right now. And so, for example, we can see that right now the replicas is actually 3, which means that the actual state of the deployment is as specified per the deployment manifest. So what I want to do right now in this video is take a closer look at the deployment resource, right? So we talked about replicas, right? Replicas under the spec section, right? The spec replicas section denote how many pods should the manager, in our case the deployment, spawn, right? So because we denote that we want 3 replicas, this means that we spawn 3 pods, and if one of these pods gets destroyed, the deployment automatically redeploys one of these pods, right? So that the total number is always kept at 3. And we then have our deployment strategy, right? So this is a little bit more complex, right? Because updating our application is definitely something that we want to do, and ideally we want to do it often, right? When you have cloud environment where you have pipelines that are running automated processes, for example, you might have an environment where with every change to your application, this triggers a deployment, right? A redeployment of your application, for example, for testing purposes, right? Into your staging server. So deployment strategy is very important for us. So what we want to make sure is that we don't have, for example, too few replicas running, right? Our application stays responsive, right? We don't have too many replicas, right? Because we don't want to starve the system of resources, right? And if the application is faulty, we want to be able to recognize that and roll back, right? Or pause the rollout because of faulty new version, right? So Kubernetes defines 2 basic strategies by default, right? We have the rolling update strategy, where the deployment terminates the pods progressively and spawns a new pods progressively, right? So for example, if we have 3 pods, then one of these pods gets terminated and one new pod gets spawned. And when the new pod is up and ready, then one of the old pods gets terminated and a new pod gets spawned, etc., right? And so the rolling update actually defines these values, right? How many pods can you terminate at once and how many pods can you spawn at once, right? And both of these values default to 25%, right? A different strategy is recreate, where simply we terminate all replicas and recreate them as fast as possible, right? So if we don't really care about progressive deployment and downtime, for example, if all we care about is making our application as up to date as possible, right? We might choose the recreate option, for example, for our testing and staging purposes, right? So the deployment strategy is mapped to our spec strategy and type, right? And so one last thing that I wanted to point out before we move on, and let me clean this up just a little bit, right? Is that, and I have omitted it before, is that we denote within the YAML resource, right? We denote the paths exactly as I've done before, right? So we have something like spec.replica section, right? So what this means is that if I go back to my resource, I take a look at where is the spec, right? So which is here, and then this is the replica section, right? So this would be, this is equivalent to saying spec.replicas. We have our strategy, right? So our strategy would be spec.strategy.type, for example. And there you can set the rolling update or recreate. Then we have our template section, right? And the template section is actually very important because the template section defines our containers, which will be managed by our deployment, right? So again, going back to our manifest, right? Notice that everything above the template section relates to the deployment itself, right? How many replicas should the deployment spawn? What is the strategy that the deployment should employ, right? Everything below the template belongs to the pods that the deployment will spawn, right? So, for example, what will be the containers within the pods that we want to spawn, right? What is the image within that pod? So this is useful to remember, this is useful to understand, right? And in fact, if you take a look at the manifest file of a pod resource, right? Everything under the template section, right, is oddly similar to the pod resource. Well, actually, everything under the spec section, right? Everything under the spec section is oddly similar to the spec section of a pod resource. And this is on purpose, right? This is entirely on purpose. And in fact, you could take a spec section of a pod resource and place it here, provided that you correct the indentation, because YAML files are sensitive to indentation, right? Provided that you fix the indentation, it should work. So this is our template. And again, we have our coordinates, right? We have our spec template, spec containers. And that's why actually we have two specs, right? So the first specification is for the deployment itself. The second specification is for the pods, right? And then we have the container's name. So this will be, right, this will be the prefix for the pods. That's fine. Last but not least, we have labels, right? So there are actually three types of labels, or three places where we have labels, right, within our manifest file. And let's take a look. Right away, we have some labels at the beginning of the manifest file, right? So where is this labels section? Well, it's above the template section. Therefore, it will likely apply to the deployment resource itself. And that's absolutely correct, right? So this label will apply to the deployment itself and has no influence on the pods. Then we have a second section that mentions labels, right? We have match labels. And let's return to that in a bit, right? Actually, let's take a look first at our third section. And this is below the template, right? We have our template metadata labels. It is right below the template, which means that this is the label that gets applied to the pods, right? These labels belong to the pods that the deployment spawns. And now, finally, we can take a look at these match labels, right? And so this is not your regular label category, right? And remember, label is just a key value pair, as we have said. It is nothing more than a key equals to certain value, right? And so the way a deployment knows which pods to manage is exactly by a label. So in this section, in this selector section, what we are saying is every pod that matches this label, right, with the key app and the value versioned hello, right? This is the label that we want to match. Every such pod will be managed by this deployment. And so this section must conform to the labels applied to the pods, right? Because otherwise the deployment would spawn pods with labels that do not conform to the match label, right? So this is how deployment knows which pods to manage. So this was our introduction on managers within Kubernetes and on deployments. Let's take a look at how deployments actually work within our Kubernetes cluster. So welcome to our first guided exercise. And in this guided exercise, what we want to do is take a look at managed pods and how we can deploy managed pods and how the managed pods behave in our Kubernetes cluster. So what I want to do right away is pause just a little bit, right? And so this is our second course in the specialization, right? And one of the prerequisites for this course is a working Kubernetes cluster, right? So we did that in the first course of the specialization. We set up our cluster and we configured our kubectl to communicate to the cluster. And so I would definitely encourage you to take a look at our first course if you haven't already. If you don't want to do that, that's perfectly fine. Either you have your own Kubernetes cluster, or we have also attached this handy set of appendices, right? So you can take a look at the appendices at the end of this PDF. And again, I would encourage you also to grab this PDF and follow along with me, go through these guided exercises, set up your Kubernetes cluster, and go through these exercises so that you actually learn how this Kubernetes cluster works, right? So we provide a set of appendices that goes through installing, configuring a Kubernetes cluster and connecting kubectl to the Kubernetes cluster. I'm not going to go through how to do that within this course, but if you are interested, take a look at our previous courses where I go through the setup and installation procedure. So returning to our guided exercise, what we want to do is essentially we want to deploy a pod, right? And we have a particular image, right? A container image. And what we want to do is we want to create a deployment. And this deployment will create a pod, or will manage a pod that will have a single container in it, which will be based off of this container image, right? So how do we do that? Well, let me switch off to my terminal application, right? And what we can do is actually use the resource generator that kubectl provides us, right? So we know that to communicate with our Kubernetes cluster, we use kubectl. To create or generate a resource, a Kubernetes resource within our Kubernetes cluster, we use the create command. The create command takes a number of arguments. The first argument is what are we creating? So we are creating a deployment. Then we specify the name of the deployment, and then we specify the image, right? -- image. And this is the image that we wanted to create, right? So let's create that. And we see that the deployment was created. So how do we get the deployment status? Well, we know that kubectl offers the get command, right? kubectl get, and then we can get some resource, right? And what resource do we want to get? Well, we want to get the deployment. So we have our deployment. The deployment is in the ready state, in the up-to-date state, right? And one is available. So this means that one of the pods should be ready and available. So let's take a look at our pods, right? And we see that one of the pods is in the running state, and within the pods, one of the containers is one out of one of the containers is in the ready state. So of course, our other ways to get more information about the deployment is with the describe command or with the -o YAML command, right? So essentially the get command and -o YAML. So let's take a look at that in our terminal application, right? So in the terminal application, of course, we can print the full YAML representation of the resource by specifying the o YAML, right? And here we see a number of interesting data, right? For example, that there are a number of pods, right? The pods have one container, and the container uses the specified image, right? We also see that the deployment has one replica. A different way to get more information about a resource is with the describe keyword, right? So instead of get keyword or the get command, we use the describe command. So describe deployment, and then we can use the name of the deployment, right? And here, for example, we can see that out of all of the replicas, one is desired, and out of the desired, all of them are up to date, right? So one is desired, one is updated and available. So this all seems good, right? So at this point, what we can do is we can actually scale our deployment to 2, right? And let's switch to our terminal application. Let's clean this up a little bit. At this point, we have only one version of our application, but because we have a manager, we can simply tell the manager, create multiple versions of the same application, right? And so the way we do that is, of course, we are using kubectl, and the command to scale an application, right, is actually scale, right? And what are we scaling? Well, the first argument that scale expects is the resource. So we are scaling a deployment, right? That's the manager for our application. Then the scale command expects the name of the deployment. So this will be the DO100 versioned hello, right? So this is our name of our deployment. And finally, we expect the number of replicas, right? So we want the replicas, and for example, we can set it to 2, right? Then we can take a look at our pods, and suddenly instead of one pod, we have two applications, right? So why is this useful? Well, suddenly we have redundancy built into our application, right? And we don't have to worry about load balancing, and especially when we have multiple nodes in our Kubernetes cluster, right? We can reroute the traffic to different nodes, and we don't have to worry about maintaining multiple versions of our application manually, right? So one thing that that we definitely want to take a look at is how the manager acts when one of the pod somehow disappears, right? There is, for example, let's imagine that one of the pods, and let's say it is the older one, right? The first pod has the age of, let's say, around 6 minutes. One of them is, let's say, on old node, right? Kubernetes node, or is somewhere in a data center where there is an internet outage, right? And we simply lose connectivity to that pod, right? So what happens when this pod simply gets deleted, right? So this is just a simulation of change of state, right? Well, we can simulate it by using the delete keyword, right? kubectl delete, and the kubectl delete expects a argument, and the argument is the name of the resource we want to delete, right? And so we can delete a pod. We have to specify the resource type that we want to delete. So we want to delete a pod with the name of the actual pod, right? So we want to delete a pod and then the name, and then we have actually deleted the pod, right? So this pod that ended with GHRV9 has been deleted, right? So what happens when I get kubectl get pods? Well, there are 2 pods, right? And notice that the first pod is our second pod, right? So the first pod is the pod that we had created before, and now we have a new pod, right? So what we can actually do, and let me clean this up, right? What we can actually do is I can create 2 terminal applications, right? 2 terminal windows, and kubectl. I can issue kubectl get pods with -w. So this will this -w means wait, right? And in the first window, I can actually kill or delete one of the pods, right? So actually, let me do it the other way. Let me do it the other way for readability purposes, and then let's delete the older node, older pod, right? So kubectl delete pod, right? And then we delete the first pod. So right away we see that a lot of output is happening, right? So one thing that I would like to say is that DO100 pod with HZN8P, right, has terminated. So we see that it has this pod has terminated, but right away, right in the beginning, a new pod has spawned with the suffix Q for DQW, right? And it was in the pending state, then the container creating state, right? And finally in the running state. So when I issue now kubectl get pods, there should be 2 pods, right? One of them should be with this suffix, and one of them should be with this suffix, right? So let me clear this up. And that's exactly what we have. So this is exactly the power of the manager managing our pods for us, right? When one of the pods gets killed or there is an error, right? The manager spawns the pod for us without the need for manual intervention. And so the last thing that we want to do is we want to take a look at how the manager helps us, right? In our case, the deployment resource helps us in updating our application. So the first things first, let's actually update our application. So just like before, let's issue kubectl get pods, right? And let's wait. Let's issue the -w option, right? So that we can see what's happening with our pods. And in a new terminal, let's edit our deployment. And so kubectl actually enables us to edit a resource. And to do that, we can use the edit command. So kubectl edit. Then we specify what resource we are editing, right? What resource type we are editing. So edit deployment, and then the name of the deployment. What we want to do is we want to update the image of our deployment, right? So we have our image, and what I want to do is update the v1.0 to v1.1, right? So the only thing I have edited is on the image line. I have changed the v1.0 to v1.1, right? And I have kept the -external, so that's perfectly fine. Now I will save and exit out of this edit mode, right? And so we see that in the output of the kubectl get pods, a lot has happened, right? And so this can be a bit difficult to navigate, right? But the important thing is that right away we have a new pod that is spawning, right? A first new pod is spawning. Once the pod is in the running state, so at this point we have 3 pods, right? 3 containers. Once we have 3 containers running, the first container, the first pod, which was the original pod, right, is terminating. So only after we have 3 containers which are in the running state, they are working, right? One of the original containers is terminating, right? And only after then the original container has terminated somewhere here, right? Because one of the new containers is in the running state. That means that a new container can spawn again, right? So this is the second new container. And once the second new container is running, then the second old container can start terminating, right? And so why is that? Why is it that basically what governs this strategy of this rollout of new pods in the deployment? Well, we can take a look, and let me clean this up a little bit, right? We can actually describe the deployment, right? And within the deployment description, we see that we have the rolling update strategy, and there is 25% of maximum unavailable and 25% maximum surge, right? So we know that there is some kind of an update strategy. The default update strategy for the deployment manager is the rolling update. And then what happens? Well, maximum unavailable of pods is 25%. 25%, 1/4, right? Of 2 is what? Well, it's 0 because we round down, right? So therefore, no pods could be unavailable before a new pod spawned in, right? And then max surge is 25%. So again 25%, but max surge runs up, right? So that we can get at least 1 pod that always spawns, and therefore that's why we always got one new pod that got spawned, and that's why we always got one new pod after we deleted our old pods. Right, so this is how you can influence the rolling update behavior. So that is it for our guided exercise. The only thing left to do is clean up, and the way we do it is simply delete the deployment resource. When we do that, and then we clean up, when we delete our deployment resource, our pods, the pods that the manager, the deployment was managing, also terminate with our manager, right? So after some while, right, after some time, there will be no pods, and of course no deployment. So I hope that this was useful for you, and that you can now see how useful and important managers are within Kubernetes. That was it for our guided exercise, and I'll see you in the next video. So welcome to our next video, and in this video, what we are going to be taking a look at is networking in Kubernetes. So in our previous videos, what we took a look at is how to deploy managed pods in Kubernetes. But one thing that you might have noticed is that despite our deploying a workload in a Kubernetes cluster, we did not interact with the workload. Right, so the workload was there in our Kubernetes cluster, but we had no interactions with it, and so that's what we are going to be taking a look at within this chapter, right? And so the way we interact with our workloads is by using networking, and so that's why we are going to be taking a look at networking. So when we deploy pods within a Kubernetes cluster, the pods get their own IP address, right? And so remember that a pod can contain one or more containers, and multiple containers within a pod communicate with each other by using localhost, right? So by using local network interfaces, they share network space, right? So multiple containers within the same pod are not isolated when it comes to network. However, multiple pods are of course isolated, and that's why they get a unique IP address, right? And within a Kubernetes cluster, each pod has to be able to communicate with any other pod, right? So for example, if a pod 1 sends a request to pod 3, right? So if a pod 1 tries to send a packet to 10.0.0.9 IP address within a functioning Kubernetes cluster, right? It will get a response, regardless of which node the pods are on, right? So within a Kubernetes cluster, it is quite standard for a Kubernetes cluster to have multiple nodes, right? Usually an odd number. So for example, 3, 5, 7, etc., right? And so in a similar way, pod 1 could query pod 2 by sending a package to 10.0.0.7, right? So using IPv4 IP addresses. So the problem that we have with this method, with this technique, is that in the real world application, right? And actually, let me make this a little bit cleaner, right? In a real-world application or in a real-world cluster, pods are very often to get spawned and recreated. Pods are very easy to get deleted and get recreated, right? So the problem with this approach is that you have to keep rediscovering this IP address, right? So what do I mean by that? Well, imagine that pod number 3, we want to query this pod number 3, and we discover the IP address of 10.0.0.9, right? However, pod number 3 gets destroyed for whatever reason, right? For example, node number 2 loses its connectivity. Well, we don't mind that, right? Because pod number 3, for example, is managed by deployment. So pod number 3 gets destroyed and recreated on some other node, for example, right? For example, on node number 3, and there is a new pod. That means, however, that pod number 3 has a new IP address, right? 10.0.0.10, for example, right? And so our pod number 1 has to rediscover our new IP address. Well, what happens when pod number 3 gets destroyed again, right? And gets respawns on node number 2 with the original 10.0.0.9 IP address. Well, we have to rediscover the fact that 10.0.0.10 is no longer accessible and that 10.0.0.9 is accessible. So how do we get around that? Well, what we want to do is we want to introduce a new Kubernetes resource, right? And the new Kubernetes resource is called a service. So a service is a new Kubernetes resource with its own manifest file, just like a deployment and just like a pod, right? And what a service enables us to do is essentially create one IP address, right? One IP address. And a service can route whatever request we send it to a set of pods, right? So to one or multiple of pods. And so essentially, whenever we send some request to a service, the service will reroute that request to one of the pods. So what happens when we were solving one of the issues that we were solving is that pod, for example, pod number 3 can be deleted at any point, right? So what that means for us is that 10.0.0.2 is no longer accessible. Well, if that is the case, then our request will not be routed to pod number 3, but will be routed, for example, to pod number 1, right? And so instead of us keep rediscovering the IP address of each of the pods, we simply rediscover the IP address of the service, right? Which provides us with kind of a layer on top of the pods, right? Routing layer. And the service will keep routing to the pods that we configure the service to route to. The service is happy to keep rediscovering the new pods for us. So whenever the pod gets destroyed, the service will be notified and will automatically stop routing to that destroyed pod. So this is very helpful to us because our application can use services instead of using pods directly. Despite the fact that we can, services are simply more convenient for us, right? So let's make this a little bit cleaner. One thing that also I would like to mention is the fact that this enables us to do something like load balancing. So for example, when we have pod number 1, 2, and 3, and we send 3 requests, right? We send request number 1, request number 2, and request number 3. Then the service by default load balances the requests such that these pods are identical, right? They are the same application, and so the responses will be identical. And so the request number 1 will be routed, for example, to pod number 1. Request number 2 will be routed to pod number 2, and request number 3 will be routed to pod number 3. The reason for that is that the response should be faster if, for example, the pods are on separate machines such that there is no resource contention, right? So if, for example, pod 1 is on, let's say, node 1, right? And pod number 2 is located on node 2, and pod number 3 on node 3, then technically speaking, if we have multiple requests, we could see some faster performance, right? If otherwise we would have some resource contention, this could solve our resource contention. So this is another benefit of our service resource. So we have multiple types of services within Kubernetes, right? By default, we create a service that is internal to the Kubernetes cluster, and this is called a cluster IP. This is the type of service that I exactly talked about just a moment ago. This is a service that simply provides an IP for the cluster, therefore a cluster IP service, right? So this service is simply available from within the cluster, and that is its only function, right? It provides the IP that is stable and routes requests to a set of pods. So what are other types of services that Kubernetes provides to us by default? Well, there are two more types of services. There is a node port and load balancer type of service, right? Node port service, node port enables you to route requests from outside of the cluster, right? So you have a Kubernetes cluster, and let's say that you want to route a request from, for example, your browser, right? So, for example, we have our browser, right? And we can route our request through the node into a service which will route it to a pod, right? In a very simplified manner. So this is a node port service. We will not go into a detail on node port service because we will use something that is called ingress, right? And we will take a look at ingress in the next lecture. And load balancer type of service enables you to integrate your services, for example, with a cloud provider or with some kind of a load balancer outside of your Kubernetes cluster, right? So these are our services. And once again, this is how we communicate, right? So instead of pod number 3, for example, communicating with pod number 1 directly, instead of that, because this is not as advantageous for us, right? If pod number 1 gets destroyed for whatever reason, we have to rediscover pod number 1's IP address or even pod number 1's name, right? Pod number 3 can simply talk to this service, right? Which is stable. Service does not get destroyed, right? And then the service can reroute the requests to whatever pods it wants to, right? Whatever pods we configure it to. And note that the service can route to pods on whatever node necessary, right? It doesn't have to be on the same node. So at this point, we know what Kubernetes services are and how we create them. The last thing that we need to know is how we actually use them. And to use a Kubernetes service, what we need is some kind of a way to discover them, right? To discover the IP address or to discover some kind of a way to communicate with that service. So my favorite way to actually use a Kubernetes service is by using the DNS, right? DNS is essentially what you do when you browse a page, right? And you enter into your browser something like example.com, right? Example.com. And what the browser has to do is, instead of the example.com, it has to translate that into something like 1.2.3.4, right? So it has to translate a name, right, that is readable to us humans, like example.com, to something that is readable to the browser, which is the IP address, right? So DNS stands for domain name resolution. And this is exactly why Kubernetes uses, for example, core DNS, right? And services are no exception, right? So let me make this a little bit cleaner. Let me delete this. Whenever you create a service, each new service adds a DNS entry, a new DNS entry, such that we can resolve this DNS entry, right? So when we create a service, and the service is named, for example, nginx-service, right? This is the name of a service. The way we communicate with that service is by using its name. And that's why in the previous video, I said that the name of the service is important. So if the service, for example, serves on the port 80, what we can do is, from the same namespace, we can actually use something like HTTP Nginx service, right? And we get some response. So within the same namespace, we can simply use the service name to communicate with that service. Within a different namespace, right, we can actually use service.namespace. Right? So if we want to communicate with a service that is in a different namespace, we use Nginx, we use the service name .namespace, for example, nginx-service and then where the service is located. For example, nginx namespace .front end, for example, would be the name of the namespace. We can also use the service name, right? .namespace. Cluster local, or the DNS name of the cluster. And then we have the fully qualified domain name, right? Which is the service name, .namespace, .service, SVC, right? That's the resource name. And then we have the DNS name of the cluster. So cluster.local by default. So this is the let's clean this up a little bit, right? So this is the way we use DNS to communicate with a service. In most cases, right? In most cases, you might use the service name, simply service, right? Simply, for example, simply nginx-service. If your applications are in the same namespace as the service, or service.namespace if your application needs to communicate with a service in a different namespace. These two are going to be the most useful, right? However, if you need the IP address of a service, there are some environment variables, right? And so within your application, whenever you spawn a pod, whenever you create a pod, within a Kubernetes, it will be injected with environment variables in the following format, right? So it will be service name _ and then some variable names, right? And so, for example, let's say that our service name is nginx-provider. And so we would have, for example, two environment variables, all capital, right? nginx_provider _service_host, right? So this is one environment variable which would get automatically injected by Kubernetes. And so this is the key, right? And the value of that environment variable would be the actual IP address, right? And then we would have the nginx_provider, right? So this is the name of the service. So the first part of the environment variable stays the same. And then we have _service_port. So what changes is, the host changes to port. And then we get the port of the service that it listens on. So for example, we have 6379. So if you need the IP address and the port for whatever reason, you can get those as well. And if you don't need them, then you can use the DNS records and communicate with the service by using DNS resolution. So that was a lot of information about services. Let's take a look at how they actually work in our Kubernetes cluster. All right, so welcome to our next guided exercise. And in this guided exercise, we are going to take a look at how we can use services to enable networking between our applications. So in this guided exercise, we are going to deploy two of our applications. We are going to deploy the name generator application. And this application exposes a functionality. It creates an endpoint at the random name endpoint, right? And it simply returns a random name. And then we will deploy the email generator application. And this application creates the random email endpoint. And the thing that we are going to be taking a look at is that the email generator actually uses the random name endpoint in order to generate the email. So let me open up my terminal, and I am already in my do100x-apps repository, right? And in this repository, we have our name generator and our email generator, right? So let's first take a look at our email generator application, right? So I can change into that directory. And what I want to do just very, very briefly, and I would definitely encourage you to take a deep look at the applications, take a look at how they function, how they work. What I just want to take a look at is how the email generator communicates with the name generator application, right? So each of these applications contains the app directory, right? And this directory contains the source code for the application. And so let's take a look at the server.js, which is the entry point to that application. We see the random email endpoint, right? This is a express.js application. We have our endpoint, and we see that we have our generate email function. This function seems to come from our generate email file, right? So let's take a look at our generate email file. And we actually have our generate email, right? So how do we generate email? Well, we first get name, right? So where is this get name function? So our get name function, right, gets name from an external service. So this is exactly what we wanted. And the get name from external service is right above it, right? So this is exactly these 3 lines. And it seems like we are getting, issuing a request to name generator URL. And so this seems to be a variable, right? Which defaults to name generator, right? Name-generator. So this is a service that should route our requests to the name generator application. So this is exactly what we need to configure our service, right? To route to. We need our service to be named name generator. It needs to serve on the port 80, right? Because we are using simple HTTP, and it needs to route to the name generator at the very least, right? So that's quite, this is all that we need for now. Let's clean this up a little bit and let's deploy our name generator application. So let me change into that directory. And so just like before, I would encourage you to take a look at the app directory, take a look at how this application functions. This application, or actually both of the applications, contain the Kubernetes directory, right? So let's take a look at the Kubernetes directory. And in the Kubernetes directory, I see the deployment.yml. So the deployment.yml actually contains a resource manifest that I can deploy to my Kubernetes cluster, right? And so this is a deployment that will manage 3 replicas of our application, right? And it uses an image with our application. So how do we actually create this resource manifest? Well, we can use both kubectl create or apply. Both are perfectly fine. So we can use, for example, kubectl apply, right? And both of these commands take an argument, right? We create or apply from a file. So we use -f for a file and then the name of the file, right? So our deployment has been created. And let me verify what is the status of our deployment. And our deployment is ready, up to date. That means that I should have 3 pods. Perfect. 3 name generator pods are running. So at this point, what we have to do is we have to create a service which will route requests to these pods, right? So what we have to do is we have to find out what port does this application serve at, right? We can do this multiple ways. One way is just to check the deployment again, right? And I actually see that it specifies a port, and the container port is 8080. So at this point, I know that the service should serve at the port 80. It should be named name generator, right? And it should lead to target point 8080. So how do we create the service? Well, we know that kubectl provides the functionality or provides the command that is called expose, right? And then the expose expects the resource type that we are exposing, and we are exposing a deployment. The deployment name is name generator, right? And then we simply specify the parameters with which we want to create our service. So then we have our port. Our port is 80. Our target port is 8080, right? Then we can specify our name. But if the name is the same as the deployment name, then we don't have to specify it because that's the default name, right? So we can create our service, and let us take a look. And we have our service, which is name generator, right? It is a type cluster IP, so it's only internal to the Kubernetes cluster. And it serves on port 80, right? So at this point, I'm reasonably satisfied with my new service called name generator, right? And so I can go and deploy my next application. So my next application is the email generator, right? And let's actually go straight into the Kubernetes directory. And I see that we have two resources, right? We have the deployment resource. And so the deployment resource is called email generator, right? Again, it has 3 replicas. It uses our image, right? And it serves on port 8081. So that's perfectly fine. Let's create that deployment. And now let's examine the service.yml. Now, because service is just another Kubernetes resource, we can actually create it from the YAML description or descriptor, right? Just like a deployment. So that's perfectly fine. And the only thing that we need is for this service to be configured properly, right? So we need that we know that the target port is correct, right? Is likely to be correct. The services port is port 80, so that's okay. And the protocol is TCP, that's fine. And then essentially all that we need is for the selector to be correct, right? So we need for our pods to have this selector app equals to email generator. So let's quickly check that, right? And we see that in the template part, the labels app equals email generator is there. So our pods will have this label, and therefore our service seems to be correct, right? So let's create our service. And let's use the create command just to switch things up. And that's perfectly fine. So at this point, I have 2 services available to me. One is the email generator, one is the name generator. Both are cluster IP and both serve on port 80, right? So the last thing that we are going to do is we are going to be creating a new pod from which we are going to be testing our application. So let me switch back to my terminal application. And let's take a look at this command, right? So kubectl run, we have taken a look at this command in the first part of this specialization, right? And this simply creates a pod. Then we are creating this pod in a new or in a different namespace, right? The -n stands for namespace. And so this is going to be a pod in a different namespace just to demonstrate how we communicate with services in a different namespace. The name of this pod is going to be curl, right? And then -it. This means that this pod is going to be interactive, right? We need the input and output, right? So the -it is the equivalent to saying the stdyn and tty, right? That's identical. Then we have --rm, which means that once the pod exits, Kubernetes will remove it. And then we have our image, right? This is a simply image that we spawn this pod with. So this is going to be UBI image. This is a Red Hat RHEL 8 image, right? And then we are executing shell on that pod. So let's execute this command, right? Okay, so at this point, I have opened a interactive shell, right? Because we have created a shell into the curl pod, right? And remember that the pod is in the -stage namespace, right? So we have our interactive shell. And then what we want to do is we want to essentially, let me open up a new terminal. and we want to query the email generator service. So how do we actually reach our application? So we can send a packet by using curl, right? And we can send our packet to some address. We can use our DNS resolution, right? So we can start with HTTP. And then let's take a look at the name of our services. We have our email generator service, right? So this is the name of my service. If I execute it like this, and we know that our application exposes the random email endpoint, right? At this point, this packet will not work because our service is not in the same namespace, right? Remember that we have spawned our pod in a different namespace. So what we have to do is we have to use a different URL for our service, right? So that our DNS can resolve it. And the way we do that is we can add the namespace in the DNS of our service. And so our service was spawned in the username -dev, right? And so there we go, right? So when I try to simply send a request to the name of the service, this did not work. And when I try to send a request to the name of the service dot the name of the namespace in which the service was created, then it did work. And of course, we cannot forget the /random email, right? So I can close my next terminal and I can exit out of this shell. And there we go. Pod curl was deleted. And that's it for this guided exercise. So all that we have left to do right now is to delete our applications. So our applications are managed by deployments. Let's take a look at our deployments. And we can delete them. So we can issue kubectl delete. What do we want to delete? We want to delete deployments, right? And then we can simply issue 2 commands, or we can delete all of them by specifying --all, right? And that means both of the deployments are deleted, and the same applies to services, right? So let's clean this up. kubectl get service specifies that we have 2 services, right? And then we can delete the service. And we can delete both services at once. So let's verify that we have no pods in our Kubernetes cluster. And there we go. So this is it for our guided exercise, and I hope that I'll see you in our next video. So welcome to our next video, and in this video we are going to be talking about ingress. And so ingress is the way we get external traffic into our Kubernetes cluster, right? So we have our pods, and pods can communicate with each other by using their own IP addresses, right? But we know that if we have our applications, we probably don't want to rely on IP addresses directly. We want to create our services, and we want to use our services for routing, right? But we don't really have a good way of routing external traffic into our Kubernetes cluster, right? So for example, how does a user from totally outside of our data center reaches our application. And this is exactly what ingress, right? Kubernetes ingress and the ingress resource tries to solve. So Kubernetes comes with the ingress extension, and ingress extension comes with something that is called the ingress controller, right? So we have the ingress controller, and ingress controller is essentially a load balancer, right, for requests. And these are external requests that come into our cluster. So let's take a look. Let's say that we have our cluster, right? And this is our Kubernetes, right? And let's say that there is a pod, right? And in a very, very simplified way, right, at the edge of the cluster, right, you can imagine the ingress controller, right? So this is the ingress controller, and it essentially handles external traffic. So let's say that we want to reach example.com, right? And so this is sent in request 1. And so let's send that to our Kubernetes cluster. Our Kubernetes cluster will route that to our ingress controller. And our ingress controller knows, based on its settings, that, for example, example.com should be routed to pod number 1, right? And let's do that. Pod number 1. And pod number 1 will send some response, and ingress controller will send some response. Let's do it a bit better. Send some response to our user, right? However, we can have a different response. For example, we could have test.com, right? Which could also reach our Kubernetes cluster. And this could be, there could be a different pod, right? Responsible for the domain test.com. And this could be pod number 2, right? And so the ingress controller again takes that and reroutes that request into our pod number 2. Pod number 2 responds to our ingress controller, and our ingress controller responds to our originator of that request, right? So that was our request number 2. So this is just a very basic introduction to the ingress controller. Usually this is outside of the control of the developers, right? This is something that the system administrators of the Kubernetes cluster have to deploy for us as the developers. And we simply use the ingress controller within our Kubernetes cluster. But it's good to be aware of the ingress controller, of its presence, and how it works and how we can use it within our Kubernetes cluster. So now that we know about the ingress router, how do we actually use the ingress router? How do we route traffic into our Kubernetes cluster? Well, we introduce a new Kubernetes resource, which is the ingress resource, right? And this resource is a standard Kubernetes resource. And so it has its own manifest file, right? Or its own YAML manifest. And so let's take a look at this manifest. So it has a kind, which is ingress, right? It has a certain name, which is perfectly fine. Not extremely important for us, but perfectly fine. But what is definitely important for us is the rules section, right? In the under the spec section, we have a number of rules. The rules takes an array, right? It takes one or multiple of rules, and you know that by this dash, right? And then essentially, what I want to focus on is the host, the path, and the path type, right? So right away, we have certain host, certain path, and path type. So there are two path types that we can choose. We can either choose a prefix or exact type, right? And exact path type means that basically we match exactly what the path and host is, and prefix means that we will match basically what we specified or anything after that, right? And so what this configuration matches, right, is this host, right, hello.example.com, right? Then we have a slash, and then because we chose the path type to be prefix, then anything that is behind it. So for example, we could have, if we sent a request with the host hello.example.com slash login, right? That would still be matched. And so where is this request routed? Well, this is specified in the backend part of this YAML file, right? And in this backend part, we see that we are actually using a service, right? And the service name is simply hello, and the service port is 8080, right? So once we have the configuration for the host name, the remaining configuration is simply where do we redirect that request, and then the router will simply redirect that request as per the backend configuration. So how do we test it? Well, this is quite simple, right? We can test it in something like the web browser. So remember that we have to use the host name, right? The DNS host name, or we can use it with something like curl if the DNS resolution works, right? Or if we have some DNS entry, right? Or we could simply specify it via header, right? So there is the host header that can also specify it if we don't have the DNS entry. So that is about it for our lecture. Let's take a look at how the ingress resource works in our Kubernetes cluster. All right, so let's take a look at how we can actually use the ingress resource in our Kubernetes cluster to route external requests to our applications, right? So in this guided exercise, we are going to deploy an application, right? This is going to be a simple hello application. It's a very simple application. It displays a very simple output, right? The emphasis of this guided exercise is going to be how to route external requests to that application, right? So the requests are not going to be from different pods, right? From different applications within the Kubernetes cluster. The request is going to originate from our terminal application, right? From our command line. So let's create our application. The application is going to use, of course, a deployment. So let me move into my terminal, and let's create our deployment. So of course we use kubectl, and by this point this is quite a familiar command, right? We are using the create command of kubectl. We are creating the deployment resource. The deployment name is hello. That is the name that we are choosing. The image for the container in the pods that are going to be managed by this deployment is the image provided in the guided exercise, and then we are spawning 3 replicas, right? So we have our deployment. Let's take a look at our deployment. So we can use the get command, right? And we have our deployment. So at this point, we can take a look at our pods. And we have 3 pods which are creating. So let's wait a little bit until the pods are in the ready state. Okay, and we have our 3 pods in the running state, which means that our deployment hello is in the ready 3 out of 3 state, right? So let's clear this up a little bit. Now we want to use our ingress resource, and our ingress resource is going to use a service as a backend. So what this means is we have to expose our deployment, right? We have to create a service for our deployment. The simplest way to do that for us right now is to use the kubectl expose command. Expose. Now, what are we exposing? We are exposing the deployment resource, right? What is the deployment resource name that we are exposing? That is the hello resource, right? And then we just need some parameters. We need ideally we would like 3 parameters, right? Which is the port, target port, and name. So the name in this case can be the same as the name of the deployment. So we do not need to provide the name. And then the only thing that we need to provide is the port. And so let's take a look in our guided exercise. We need to create a service that listens on port 8080, right? And redirect the traffic to port 8080 within the pod. So when we have the target port and port of the service identical, all we can do is simply specify the port, right? And when we specify only one port, kubectl and Kubernetes assume that the target port is the same as the port that we specify. And so both port as well as target port is going to be 8080, right? So we can do that. And we have created the service hello, right? We can actually describe this service. And so just like we expected, the target port is actually 8080, and we are routing to several endpoints, right? These are our pods to port 8080. And there are 3 endpoints because we have 3 pods. So this all looks well and good. And up until this point, this is all familiar territory, right? So right now we have to create our ingress resource, right? So I am in the do100x-apps directory, right? This is our GitHub repository. And in the repository, we have a handy network directory. So let's change into that directory, right? And let me actually make it a bit cleaner. And in this directory, there is the ingress-hello.yml file. So let's open it up in an editor, right? And so this is a simple ingress manifest file, right? This is exactly what we were discussing in our lecture. And so the name is hello, right? That's perfectly fine. The kind is ingress. That's exactly what we want. And the first thing that we might notice is that the host is ingress host, right? This one we have to change. So we'll get to that in a little bit, right? Then we have our path. So that's quite fine. We have a / path. The path type is prefix. So this is also what we would like. We would like all of the paths to match, right? And then all of the requests will be routed to a service with the name hello on port 8080. So this is exactly how we configured our service. So what should be this host path? So if you have configured the Kubernetes cluster with us, right, in the previous course or in the appendix, we have actually configured the host name, right? And so on this system, I have configured the Minikube IP to the hello.example.com host, right? And so this is exactly the host that I'm going to be using, right? And if you haven't configured this, there are two configurations that you must perform for the ingress guided exercise to work. You have to enable the ingress add-on on your Minikube cluster, and you have to configure the Minikube IP to some host in your hosts file, right? And this is all in the either in the previous course or in the appendix, right? So let's take this host and let's open up our ingress hello, and we can delete this, and the host is going to be hello.example.com, because this is the host that reroutes on my machine to the IP address of the Minikube, right? Or resolves rather. There is the DNS entry for this host. So this is all well and good, and that is the only configuration that we need to make. So let's save and exit, right? And once we have that, once we have our ingress hello.yml configured, we can create it like any other resource, right? So how do we do that? Well, we have the create or apply commands. So let's use our apply command. And like usual, we use the -f for file, right? And there we go. We have our ingress, right? So let's query for the ingress file, or ingress resources rather. And we have our hello ingress, right? So we have our hello.example.com, which is a new ingress that is in our Kubernetes cluster. So the only thing left that I have is to actually check and verify whether the ingress works. So we can do that by using something like curl. And what are we curling? Well, we are trying to send a request to this host, right? And so we can do that, and we got a response, right? So we got a response from our actual pod within our Kubernetes cluster, right? And we can actually remove that, remove the slash. That is all perfectly fine. And so as we send our requests to the host, right, the ingress controller is rerouting our request to the pods, right? And we are getting responses, that contain the IP address of the pod that actually responded to our request. So how do we know that our pods actually responded to the request? Well, we know that the IP address that responded to the pod, or the pod's IP address which responded to our request, is 172.17.0.5, 6, and 4, right? These are three addresses that we are constantly getting. And so let's actually describe our service one more time, right? And when I describe the service named hello, which is the service for our application, we see that this is exactly the IP address of the pods which the service routes to, right? 172.17.0.4, 5, and 6, right? Which is exactly the IP address from which I get my response. And in fact, I can also issue kubectl get pods with the white output -o white, right? And get the IP addresses here. And if you are using the OpenShift Sandbox environment to actually go through this course, you might have difficulties actually fitting out the host path of our ingress. So let's take a very quick look at that. For this part, I have switched to the OpenShift Sandbox environment, and I have actually deployed our application into that environment. And let's take a look at our ingress resource, right? So I have already filled out my host path, right? And let's go through how I figured out what the host path is. So the first part of the host, right, consists of multiple things. So it consists of the name of your resource. Our name of the resource is hello, right? Separated by a dash. Then we have our namespace. So this is going to be your username -dev, right? This is our namespace. Then it's going to be a full stop or dot, right? Then we have apps, full stop. And then the last part is going to differ for you, right? So this .apps .something, this is the wildcard DNS entry of the OpenShift router, right? And this you have to find out, right? This you have to figure out. And so how do we figure out the last part, right? This is the difficult part to get. And so the easiest way to actually get to the domain of the OpenShift router is to open up the OpenShift console, right? Click your username, copy login command, right? And then within the copy login command screen, you'll be presented with the OC login command, right? And then we have --server. And so with this --server, what I have done is I have taken the actual DNS part, right, or the domain part, and instead of the API, right, it starts with API full stop something, right? We have effectively changed the API to apps, right? So I have disregarded the API and taken the rest. So the sandbox, it starts with sandbox, and ends with openshiftapps.com, right? And we disregard the port number. So we have taken the sandbox, M2, etc. So this part we have taken and appended after the full stop apps, full stop, and then we have our sandbox part. So this is how we can create our ingress in the cloud environment, right? And so I already actually have it created. So let's take a look at our ingress, right? And we have our host. And just like with our Minikube, I can curl it and get a response. So this was it for our guided exercise. The only thing that we have left is to clean up our namespace. So what did we create? Well, we created our ingress, right? And we created our deployment. And how do we delete these resources? Well, we can simply use the delete and use the -- all flag. And there we go, right? The deployment resource will delete all of the pods. So we can verify that there are no pods, and we can verify that there is no ingress in our namespace. And one last thing that we can't forget is the service, right, that the ingress resource used. So we have our hello service, which we can delete in the same way. kubectl delete service hello. And we have no more service in our namespace. So at this point, I hope that you understand how we can route requests from outside of our Kubernetes cluster into our Kubernetes cluster. And I'll see you in the next video. Welcome to our next lecture, and in this lecture we are going to be talking about limiting usage on our Kubernetes cluster. And the first thing we are going to talk about in this lecture is limiting resources on pods, right? And so we know that pods are essentially containerized processes, right? Kubernetes does not use containers directly. It wraps containers in pods, right? And a pod is one or multiple containers, right? Wrapped together. And so a container is essentially a process that is isolated from the rest of the system, right? We isolate the process. And so since the process is already isolated, the question arises of, can we further restrict the process in some way, right? Can we restrict, for example, the amount of memory that the process can use, or can we allocate some memory to the process, right? And the answer is yes. So how do we do that? Well, within Kubernetes, we have two main concepts for pods, and we have resource requests and resource limits. And the way we can think of these, right, is essentially that resource requests request the least amount of resources that the pod requires, right? So essentially with resource requests, we say to the node that this pod should not run on a node that does not have sufficient resources, right? And resource limits is the opposite, right? Resource limits actually limits the resources that the pod can use, right? So with resource limits, we say to Kubernetes, do not let this pod consume more resources than we configure. right? So let's take a look at a resource manifest. So we have our YAML file, and this is a YAML file from a deployment. We have our spec file. Within the spec file, we have our containers, and we have our first container object. And within the container object, we have our resources. And within the resources, we configure requests and limits, right? So the requests, we configure that this particular container will require at the very least 10 CPU millicores and 20 megabytes of memory, right? And in the limits part, we configure that this container shall not exceed 80 millicores and 100 megabytes, right? And so at this point, you might wonder, what is this millicore unit? And so in Kubernetes, Kubernetes uses this unit of millicores, where basically one CPU is equal to 1000 millicore, right? And so the CPU can be a virtual CPU or a physical CPU, depending on the host. So how do we set these resources? Well, we can edit the YAML file directly, the descriptor directly, right? Or we can actually use a new kubectl imperative command, right? We can use the set command. Then what are we setting? Well, we are setting resources, right? And then the kubectl set command expects the resource type, right? So we are setting the resources on the deployment, and then the deployment name. So in our case, for example, it could be Hello World Nginx, and then simply we configure the actual resources. So for example, -- requests, and we configure the requests as per the YAML file above, right? And then we can configure the limits, right? So how do we view the requests and limits? Well, we can view it, of course, per individual pod, right? But maybe a nicer way is to describe a node, right? And what you can see within a node is basically all of the requests and resources of all the pods that a node hosts. So essentially, within a Kubernetes, a node is a machine that runs the Kubernetes platform, right? And it hosts a number of pods, and then you can actually see the CPU requests, right? Memory requests and limits for each particular pod that the node is hosting. And then we can see the total, right? Total of requests and limits below. And then if you have installed the metrics API, then you can actually execute the kubectl top command, right? And view this metrics via kubectl. But again, this requires you to have additional controllers deployed on your Kubernetes cluster. So at this point, we know how to limit the resources of individual pods, right? Of individual processes, in essence, right? However, the problem that we might want to tackle and what we might want to solve is what if we have one Kubernetes cluster that multiple teams are using, right? Let's say that we have one organization, we have one company where we have tens, hundreds, sometimes even thousands of teams, right? Small atomic teams. We can have even just one large Kubernetes cluster, and we want some way of limiting how many resources can one team consume within our Kubernetes cluster. So restricting the usage of individual pods of the resources does not really solve our problem, right? Because team A can spawn, for example, 50 containers that request very few resources, right? But team B can spawn one container that requests, for example, 50 gigabytes of RAM, right? And so this is something that we have to handle some other way. And so we have the concept of quotas within Kubernetes, right? And quotas enable us to configure a number of limits, right? We can limit the object counts, and we can limit the compute resources, right? And so object counts limit exactly the number of Kubernetes resources that we can spawn, that we can create. For example, number of pods, number of services, etc. And compute resources limits the number of resources that we can consume within, for example, a namespace, right? So for example, how much CPU, right? How much CPU, memory, storage capacity we can use. And this should prevent, the aim of quotas is to prevent contention for resources within multiple teams, right, on one Kubernetes cluster. And so the way we apply or use quota is by using a new Kubernetes resource, which is the resource quota, right? And so this resource has its own manifest file, right? This is a new kind. It's called resource quota. And just like usual, it has a spec, right? And within the spec, we set some kind of a quota. And so within the quota, we can set either the resource name, and then we describe, or we are setting how many of these resources can we spawn, right, within a namespace. So for example, if we specify pods, right, if we specify pods and then 10, that means that we can create only 10 pods within that namespace, or we can specify some compute resource name, such as request CPU, request memory, etc. And then this means something like total usage of that resource across the containers, right? So this is exactly what we have here. We have services 10, right? So this means that within this particular namespace, only 10 services can be created. All of the containers can use at most 1.3 CPUs, right? And 1.3 GB of memory, right? So then once we have our YAML file, we know what to do with it. We can create it just like every other resource by using create or apply, right? Alternatively, we can use our resource generator within kubectl, and we can use kubectl create. Then kubectl create needs to know what are we generating, what resource are we creating, and we are creating a quota, right? And then we simply provide the name of the quota, right? So this is a dev quota, and then we specify the parameters. So there is a hard quota of 10 services and CPU and memory, right? 1.3 CPU and 1.5 GB of memory. And once we create this resource, it is a standard Kubernetes resource. So we can issue kubectl get command, right, on the resource quota. And we can take a look at all of the quotas that are available within our namespace. Last but not least, there are some there are some caveats with creating quotas, right, which I would definitely encourage you to take a look at within our handy PDF. So for example, if you are creating a quota in a namespace with existing resources, right, the quota might not affect already existing resources. If you are modifying, right, if you are modifying a resource that would exceed a quota, then the modification is denied, right, etc., etc. So take a look at the PDF. One thing I definitely wanted to point out, though, is that quotas are very useful for us as developers, because though we might not create a lot of quotas, right, we will definitely encounter a lot of quotas in real world, and it's definitely very useful to know why some of our actions are being denied by the Kubernetes cluster, right? So when there is some kind of a action that is denied, it might be helpful to take a look at the resource quota or quota and see whether there is some kind of a namespace bound quota that restricts me, and what the actual quota is. The last resource we are going to talk about today is a limit range. And as the name suggests, a limit range enables us to define a range of acceptable values for our limits and resource requests, right? So let us first take a look at the resource YAML syntax, right? At the resource manifest. And then let's take a look at the problems that the resource is trying to solve. So this is a complex limit range that we have here in front of you. This is a new kind, right? We have our limit range. And so this is a new Kubernetes resource, Kubernetes object, right? We have our name, which is perfectly fine. And then we specify in the spec section, we specify the limits. And the limits we specify for different Kubernetes resources, right? We specify the limits for example, pods or containers, for persistent volume claims, etc., etc. And so what I want to take a look at is this container type, right? So right here, this is the section that I want to focus on, I want to hone in. And within this section, what does this section tell us? So we are in the limits, right? And we are specifying the range of the limits. So the maximum value that we can set for the container type, right, is 500 millicores and 750 megabytes of memory. So this is the maximum value for the limits, right? However, we can also set minimum values for limits, right? So at the minimum, the limits should be 10 millicores and 5 megabytes of memory. And then if we have a container which does not specify any limits, then we can set some default limits. So by default, every container will have certain limits, which will be 100 CPUs, CPU millicores, I mean, and 100 megabytes of memory, right? And last but definitely not least, we can configure default requests. So when we spawn a container which does not specify any requests, right, we can automatically configure this container to specify 20 millicores of CPU and 20 megabytes of memory, right? So this is the This is exactly what the limit range allows us to do. It allows us to specify, and let's clean this up a little bit, right? It allows us to specify the range of maximum and minimum values, right? That's the range. And then it specifies, it enables us to specify the default values for both the limits and the requests, right? So why do we want to do that? Well, number one, right? We don't want to have containers, for example, containers, which would specify their limits to be, let's say, 4 CPU cores, right? Let's say that we are in a Kubernetes cluster that is used by a company that has multiple teams. Let's say it has tens, even hundreds of teams that use one Kubernetes cluster. Well, we don't want one team to be able to create containers which can consume more than half a core. Well, this is a way to enforce it, right? In a similar way, we might not want one team to be able to create containers that consume more than a certain amount of memory, right? So we can specify what we consider a reasonable range of limits, right? And then we can also specify when developers do not specify any limits on their containers or any requests on their containers, we can actually configure it for them automatically, right? We tell Kubernetes if the developer does not use any values, we'll set it for them, and these are the values that are going to be used, right? So this is very useful, and again, as a developer, this is something that is very good to be aware of, because this essentially changes the way your application might behave in a production environment, right? So when you are deploying your application to a cluster that you do not know, maybe it is good to be aware of limit ranges and aware of these restrictions. So once we have this manifest, what can we do with it? Well, we actually know what we do with it, right? It's an object like any other object within Kubernetes. Once we have our manifest, we can use the create command of kubectl create, right? Which will create our Kubernetes object, our Kubernetes resource. And then, just like any other Kubernetes resource, you can get more information about the Kubernetes resource by using kubectl get or kubectl describe, right? And so here, for example, we can see that we have configured the pod configuration, right? So we have restricted the CPU resource on pods, right? At least 10 millicores, at most 500 millicores, as per the YAML configuration above, right? And this is all within a certain namespace. And if you have the privileges, like any other resource, you can, of course, delete it. So this was an introduction into limiting resources on a Kubernetes cluster. And let's take a look at how we can actually do that on our Kubernetes cluster in our guided exercise. All right, so welcome to our next guided exercise. And in this guided exercise, we are going to take a look at how the limiting resource usage works in an actual Kubernetes cluster. So what we are going to do is create a deployment within our Kubernetes cluster and request too many resources and take a look at how our Kubernetes cluster deals with that deployment, right? So let me switch to my terminal application and let me create the deployment. And we have our kubectl command, we are creating a deployment resource with the name hello limits with the provided image. We want to simply print the generated resource, right, in the YAML format, and then we are redirecting it into the hello limit.yaml file, right? So then I can open the file, and within the file, we want to edit this file such that we edit this resources section at the bottom, right? So for this one container that the resource generates, we want to add some resource requests, right? So what are we requesting? Well, we can request, for example, something like 8 CPUs and 20 megabytes of memory. So that's perfectly fine. So remember that when you are editing a YAML format, the white spaces are very important. So within the resources, what you want to do is you want to add 2 spaces to the right? And then you want to add the requests, right? And then within the requests, again, you want to add 2 spaces to the right and add CPU. And then let's add 8 CPU cores. And then in the same line, we want to add memory. And that should be 20 megabytes, right? So we have our resources, our requests, CPU, and memory. So this looks good. Let's save this file and see how our Kubernetes cluster deals with this deployment. So we can create this resource. And so this deployment has been successfully created. And let's take a look at our pods. And this pod is in the pending state, right? And so there are several ways of how you can troubleshoot a pod that is not spawning, right? That is still in the pending state. One of the ways is, for example, you can describe the pod, right? And right away, we see that there are some events for this pod where the pod has failed scheduling, right? Because there is an insufficient CPU, right? So there is no node which provides 8 CPU cores for the pod. In other words, the pod is too big for any of the nodes in our Kubernetes cluster when it comes to CPU, right? So another way of troubleshooting our failing pod scheduling, and let's clear this up, is kubectl get events, right? So we can actually get all events and filter for warning type events, and we have some failed scheduling events. So this is all good, right? So how do we alleviate this this issue? Well, let's try to actually edit our hello limit.yaml file. Instead of 8 CPUs, let's try to schedule 1,200 millicores, right? Let's see if that helps us. And let's modify our deployment, kubectl apply, right? And so our deployment is configured, has been modified. So let's take a look at our pods right now. So kubectl get pods. And at this point, I still get the pending state, right? So my Minikube still does not get 1,200 millicores, right? The nodes in my Minikube cluster simply do not have even 1,200 millicores for a pod, right? So let's verify that. Let's describe the new pod, right? Let's describe the new pod, and it still is failing scheduling, right? So let's see our YAML file again. And let's modify this. Instead of 1200 millicores, let's modify this to 120 millicores, right? So this is substantially smaller container image or container. And let's apply this. And at this point, let's take a look at our pods. And we see that we have only one pod and it is in the running state. So that means all of our previous pods were in the pending state. However, because we have our third iteration which succeeded, our pending pods are identical, right? And therefore were terminated because this pod has superseded our previous configurations. So there we have it, limiting resources by resource requests and resource limits. All we have to do now is clean up our cluster. So let's delete our resources, and actually we have a new way of deleting resources. We can issue kubectl delete, and instead of specifying the resource name, we can actually specify our file, right? So just like kubectl create and apply, with delete, kubectl delete, we can specify -f and simply specify the file name. And this means that my deployment is deleted. So that's it for this guided exercise, and I hope that I'll see you in the next video. So welcome to our next lecture, and in this lecture we are going to be talking about proving whether our application is ready to serve requests. Right? So far we have been deploying our applications to our Kubernetes cluster. However, we have had no way of determining what is the status of our application. Right? So far, the only state of our application that we were able to ascertain was whether, for example, the node that was hosting our application was alive, right? And so if our application was managed by some kind of a manager, for example, a deployment, and the node would go down, right? The deployment would discover that and redeploy our pod. Or alternatively, if the whole process, if the whole container, right, exits in an error state, the deployment would redeploy that container, right? However, what we want to do is we want to have a more granular approach of determining some states of our application, right? And so this is exactly what we are going to be taking a look at within this lecture, right? So what are we going to want to determine, right? Well, we might want to determine, for example, something like a temporary connection loss, which might result in an application that is unavailable, right? That becomes unresponsive for a short period of time, right? So, for example, an application requires a connection to a database, which is located outside of that application pod, right? And the application cannot get to that database, cannot connect to it, and therefore it becomes unresponsive. However, when that becomes resolved, the connectivity becomes resolved, right? Our application comes back online, right? So what we want is essentially a way to reconcile this state. We also want to take a look at some application errors. So for example, our application works, right? And it works until it does not, right? So for example, there is some memory leak. We keep serving requests, and suddenly our application freezes, right? And stops serving requests. So what do? Well, we probably want to restart our application. I mean, ideally we want to fix our application, right? But in the moment, right, in that particular moment, as an immediate hotfix, right, we want to restart the pod, and of course we want to fix our application source code. But within the application pod, what we want to do is restart that pod, right? And configuration errors, those are there are many ways that those can resurface, right? So what does actually Kubernetes give us to take a look at checking the state of our application? Well, Kubernetes gives us probes, right? And there are several types of probes that Kubernetes provides us to check us the state of our application. One such probe, or the first probe that we are going to take a look at, is the startup probe, right? And in essence, the startup probe is executed at the beginning of the life cycle of the pod, right? So we deploy our pod, and then we configure the startup probe right as the pod comes online. Essentially, the startup probe executes, and the pod will not be considered to be ready to serve requests until the startup probe passes, right? Once the startup probe passes, the pod is ready to serve requests, and the startup probe will no longer be checked or verified, right? So, for example, let's consider that we want to deploy a database application into our Kubernetes. So this is, for example, for development or staging purposes, right? We have our containerized database process, which is perfectly fine for something like development purposes, and it takes a while, despite the process to come online. Right? It takes a while for the database to be ready to receive connections, right? So the process is ready, but the database still requires some time to process connections. Well, this is exactly what the startup probe does, right? And once, for example, the first SQL command passes, then the startup probe passes, and then we assume that the pod is ready to serve other requests. But once the first command passes, startup probe is no longer useful to us because we simply assume that all other SQL commands or all other connections will be successful. So what happens if the startup probe does not pass? Well, the container, there is a threshold, right? There is a certain threshold of failures. If the startup probe does not pass a certain amount of times, the pod is considered to be faulty, right? And we have some kind of a restart policy. So, for example, we can restart the pod because we can assume some kind of a failure, and until the startup probe passes, there are no requests sent to that pod, right? So this is a startup probe. Then we have two other types of probes. We have a readiness probe and liveness probe, right? So let's start with our readiness probe. And readiness probe essentially says, is the pod ready to serve requests, right? So essentially we have our application, right? We have our process, and what we want to do is determine whether we should route requests to that pod, right? So readiness probe is a probe that runs continuously throughout the pod's lifecycle. So unlike these two probes, readiness and liveness probe, unlike the startup probe, right? Startup probe runs once, and once it passes, it no longer runs. Readiness probe runs continuously, right? And until it passes, the pod is marked for readiness probe. If it fails, the pod is marked not ready, and therefore no requests are routed to this pod, right? Once it passes, the pod becomes ready, right? So that's all well and good, and Kubernetes routes requests to that pod, and throughout the life cycle of this pod, right, this readiness probe is continuously evaluated, and if the readiness probe becomes inactive, right, fails again in the future time, then the pod is marked not ready again. So this is the main difference, right? And then we have our liveness probe. And liveness probe detects the unhealthy state within an application, right? So this is the probe that tries to determine whether the application, for example, has some kind of a memory leak or some kind of a state that made the application freeze but not exit, right? Or something similar. And so liveness probe again is continuously evaluated, right? And when liveness probe fails, the pod is detected unhealthy and restarted, right? Redeployed, restarted. So the summary, right? We have 3 probes. Startup probe, right, is executed once at the beginning of the lifecycle. Once it is passed, it is not executed again. Readiness probe is executed continuously. Once it fails, the probe is marked 0 out of 1. For example, if there is 1 container within the pod, right, it is not ready for requests, but it is not restarted, right? And then we have liveness probe. If the liveness probe fails, the pod is restarted. And then, of course, we have a number of options, right, for each of these probes. So, for example, we can configure what is the failure threshold for each of these probes, right? So the fact that one probe fails once might not mean that the pod is faulty, right? Sometimes it might take a while on certain systems, right, for a process to come up. We might also set something like a success threshold, right, etc., etc. So we have a number of parameters with which we can fine-tune these probes such that they work for our applications. So at this point, we know how probes work in Kubernetes, and let's take a look at how we can implement them, right? So we can implement each of these probes by several methods, right? A very common method of implementing any of the probes within Kubernetes is by using HTTP checks, right? So a lot of the applications that we deploy on Kubernetes expose some kind of HTTP interface, right? Such as something like REST API, right? Where essentially the application uses an HTTP interface or HTTP API to communicate with other applications, right? And so the probes can actually use this API in order to determine the status of the application, right? So we can actually issue within, for example, this particular example uses the readiness probe, right? And we'll take a look at how we can configure the probes in a bit later, right? But here we configure the readiness probe. We are configuring the get request, right? This is an HTTP verb, and we configure a certain path within that pod, right? Within that application, and we specify on which port, and then we configure the parameters that we talked about in the previous video, right? So we wait initially for 15 seconds before executing the first request, and we configure a timeout of 1 second. So HTTP checks, extremely common as a way of implementing probes within Kubernetes, right? Very useful, very easy to implement within your application as well, if your application already exposes some kind of HTTP based API, such as by using REST API, right? We then have something like container execution checks, right? So what does this mean? Well, you actually execute some kind of a command within the pod, right? So for example, just to switch things up, we have a liveness probe, right? And then we configure the execution check, right? We have our exec check, and then we execute a command, and the command is in a form of array. So essentially, we have a multiple objects, right? Multiple strings in our case, where we place a command that will be executed within the pod. So why is this useful? Well, for example, let's think back to our example about the database, right? If we want to wait for our database to be able to execute an SQL command, well, we could actually wait. We could actually use something like the container execution check and use the tools within the container to execute something like select one, right, within the container. And once this command passes, right, we can actually assume that the database is ready to accept connections, right? Another way of implementing our probes is TCP socket checks, right? And so if, for example, your application does not expose HTTP interface, but still communicates via something like TCP ports or TCP sockets, right? Then you can, of course, use TCP socket checks, right? So the way you do that is by using the TCP socket, right? And then all you have to do is specify the port. And if the probe can connect to that port, right, then we assume, if it can establish a successful connection, right, we assume that the check actually passes. And if it cannot establish a successful connection, then the check fails, right? So these are 3 very common ways of implementing our probes. So these are the most common ways of implementing probes within Kubernetes. So how do we actually use them in Kubernetes? Well, that's extremely easy. We can actually edit something like a deployment, right? So for example, we can execute kubectl. The edit command will actually edit a resource. We can edit the deployment resource. Then we specify the name of the resource, right? And then for the particular container, right, we can add the probe type, right? So we have our readiness probe, liveness probe, or readiness probe, liveness probe, or startup probe, right? And then we specify our parameters, right? We specify our parameters, for example, here, as well as here. And then we specify our probe implementation, right, which is over here. And let's clean this up a little bit. And in this case, we are implementing the probe by a simple HTTP GET, right? So this is an HTTP check at the endpoint of /health_z, right? So this will be executed at the endpoint of the container, or at the endpoint of the pod level, with this particular port, so port 8080 and scheme HTTP. So that's perfectly fine. So now that we know how to implement liveness, readiness, and startup probes, let's take a look at how it actually works within our Kubernetes cluster in the next guided exercise. So welcome to our next guided exercise, and in this guided exercise we are going to take a look at liveness and readiness probes in our Kubernetes cluster. So we are going to be deploying a simple application, right? And this application exposes 2 endpoints that we are going to be using for our probes. One of these endpoints is /health or healths. And this is going to be used for the liveness probe. And then we have /ready endpoint, and this is going to be used for the readiness probe, right? And so these probes are implemented by the HTTP probes. And what is special about the /ready endpoint is that it takes around 30 seconds after the start of our application for it to return a successful status code, right? So for the first 30 seconds of the runtime of the application, it returns 503, which is considered a failure status code. And after around 30 seconds, it returns 200 HTTP code, which is considered a success, right? So let me open up my terminal application and let's create our deployment. So I can create my deployment by using the kubectl command, right? And this is, by this point, this should be quite familiar. We are using the create command, creating a deployment resource with the name do100-probes. And we are using the image that is provided in the guided exercise, right? So we have our deployment. Let's take a look at our deployment. And we have our do100 probes ready, up to date, and available, right? So we are going to be interacting with our application. That means I have to expose this deployment. So let's do that. And we are exposing the deployment with name do100-probes. And the port of this service that I'm creating is going to be 8080. The application also serves on the port 8080. So I can simply omit the target port. And that is all that we need. And the name of the service is going to be do100-probes as well. So we can create it, and we have our do100-probes service. So at this point, what we need is an ingress resource, right? Because we are going to be interacting with our application. I am in my do100x-apps repository. And so in this repository, there is the probes directory. So let me change into that directory. And within the probes directory, there is the probes-ingress.yml resource. So let's take a look at the resource. And within that resource, let's just double check that it is correct. So we have to double check the host for our ingress. If you are using the OpenShift environment in the cloud, you have to set your host. And if you are unfamiliar with that, refer to one of our previous guided exercises. Then for the path, we definitely want a slash. That's perfectly fine. For path type, we have to use the prefix. And for the service, we have to use the correct name, which for us is DO100-probes. And the service serves on the 8080 port. So this looks like a correct ingress to me. So let's create this ingress. So I can simply execute kubectl create, and my ingress has been created. So let's clear my terminal, and let's try to reach our application. So let me take a look at my ingress, and we have our host, and I can try to curl my host, and I get a response from my application. So at this point, I have deployed my application. Everything is well and good, right? And we can start taking a look at our probes. So let's take a look into our guided exercise. And essentially, what we need to do is we need to configure the liveness probe, right? To use the health endpoint on port 8080, the readiness probe to use the ready endpoint on port 8080, right? And then we have some parameters like initial delay of 15 seconds and a timeout of 2 seconds, right? So where do we configure these probes? Well, we configure these probes on the container, right? Where do we configure our container? Our container is managed by a deployment, right? So we can actually either execute kubectl edit the deployment, right? Or what I find a bit easier is essentially executing something like kubectl create deployment. So we generate our deployment by using the dry run client and output YAML, right? And redirect the output into a file. And then within the file, we scroll down into the container section. And within the container section, we configure the probes, right? So we configure the readiness probe as well as the liveness probe. Now, one thing I definitely want to make you aware of is the indentation, right? So whenever you are editing a YAML file, right, the indentation has to be exact. So number one, do not use tab files for indentation. Use spaces, right? And number two, be very careful so that, for example, the path and port are indented at the same with the same indentation, right? Whereas, for example, the HTTP GET is indented with the same indentation as initial delay seconds, right? So make sure that the parameters align properly so that the YAML objects are created correctly, right? So we have our readiness probe. Then we have to add a new line, indent 2 spaces to the right, write HTTP GET, right? And continue again, add a new line, 2 spaces to the right, path, right? / ready, etc., etc. So once I have my file complete, let me save this file, and I can actually apply my deployment. I can configure my deployment. So I can do that by kubectl apply. And the warning is perfectly fine. However, the deployment is configured. So what happened now? Let's take a look at our pods. And one of the pod is in the running state, and it is of age 7 minutes. So this is an old pod, right? We have a new pod of age 13 seconds, and it is in the ready 0 out of 1 state, right? And it is still not ready even after 29 seconds. So why is that? Well, remember that the ready endpoint takes around 30 seconds to return a successful state, right? To return an HTTP code of 200. And then we have some initial delay of 15 seconds, right? So returning to our terminal, only after, let's say, around 45 seconds, our new application pod becomes ready. And only after our new application pod becomes ready, the old application pod terminates, right? So this is exactly what the probe does. It does not terminate old pods until new pods are ready, and new pods are not ready until our readiness probe passes. So at this point, what I want to do is I want to explore what happens when the two probes that we have configured start failing, right? So I have opened a new terminal, and from this new terminal, I'm going to make the two probes fail. So at this point, let's take a look at our pod. We have one pod, and let me take a look at the logs, right? Let me print the logs of this pod. So that's kubectl logs -f for follow the logs, and the name of the pod. And in the logs, we can actually see how the probes keep interrogating the endpoints, right? The /ready and /health endpoints, and we keep getting the success responses. So we keep getting the ready and healthy responses. So what happens, for example, when I make the health endpoint return a fail state, right? So the app state is switched to unhealthy, right? The health probe is returning the unhealthy state, right? The fail state. And so the liveness probe, right, it starts to fail. Well, from our lecture, we know that when a liveness probe starts to fail, what happens? Well, our pod restarts, right? And after 3 unhealthy responses, we get 1 restart, right? So kubectl get pods, and we have 1 restart of our application pod. Now, of course, because we get a restart, the pod is in not ready state, because at this point, our ready endpoint has a 30-second delay, right? Just like in the beginning, and has to get ready. So this simulates kind of a slow startup of the application, right? And so at this point, our application is ready again, right? Is ready 1 out of 1, is running, has still 1 restart, and is ready to receive requests. So this was the liveness probe that received a failure. What happens when the readiness probe receives a failure, right? So let's do that again. Let's see the logs of the pod, right? And we see that the ready and health endpoints are showing the success states, are returning the success states, right? And so we actually can issue not kill health, but the kill ready command, right? And so we are killing the readiness probe, right? So what does this mean for us? Well, the health probe still returns a healthy state, right? But the readiness probe returns not ready anymore, right? So there is a first not ready, right? There is a second not ready, and there'll be a third not ready, right? However, what happens when the readiness probes fails? Well, from our lecture, we know that when the readiness probes fails, the application pod does not restart, right? The application pod simply becomes not ready. So what does that mean? Let's get out of the logs and let's take a look at our pods. So our pod still has only one restart, but is marked as not ready, right? And so what does this mean? Well, at this point, if we want to issue any more requests to it, we can't, because Kubernetes marked the pod as not ready, and therefore the Kubernetes service does not route requests to this pod. And therefore, the ingress does not have any backend to the service and has no endpoints for our request, right? So this is the behavior of the probes within Kubernetes. So now that we understand the behavior of probes in Kubernetes a bit more, the only thing left is cleanup of our cluster. So we can actually delete all. Delete all resources within our Kubernetes cluster. So we can delete our deployment, our service, our pod and replica set. That's perfectly fine. And after that is done, we have to delete our ingress as well. So this concludes this guided exercise, and I'll see you in the next video. So welcome to the next lecture, and in this lecture we are going to be taking a look at configuring our application in Kubernetes. So when we develop our applications, it is very common to develop our application in one environment and deploy the application in a completely different environment, right? So let's take a look. This is a three-phase environment, right? Where, for example, I code my application in something like a dev environment, right? And this is where I can do whatever I want with my application. And then once I feel like my application is ready, I can promote the application into a stage environment. And for example, in the stage environment, something like a QA team is taking a look at the application, but also it doesn't have to be a QA team. There can be an integrated suite of tests, right? Integration tests that runs against this application that either passes or fails, right? And depending on the state of the suite, I can demote the application back into my dev stage or promote my application into the prod stage, right? Into my production environment. And these environments can be completely different Kubernetes clusters. It can be one Kubernetes cluster in different namespaces, right? And this is just an implementation detail, right? However, a thing that can definitely change and will most likely change is, for example, a database, right? So what if my application depends on a database? Well, in the dev environment, I probably have my own database with a very small set of data, right? While in the stage environment, well, if there is a suite of tests, it probably comes with its own database, right? So my application has to connect to that database. And the suite of tests will probably modify the database as it will deem necessary, right? And in production, right, we definitely have a separate, completely separate database, right? That I, as a developer, probably don't have access to. It might be even external to Kubernetes completely, right? So how do I make my application ready to deploy across multiple environments, right? And ready to connect to multiple databases? Well, what I definitely don't want to do is hard code this database string, for example, right? This connection. If I hard code it into my application source code, what I have to do is after or before actually every promotion, right? Before every change of the environment, I have to change and recompile my application, right? So what it does is it actually invalidates, right? It invalidates this testing suite because I actually change what my application is. So I cannot say for certain that this application has passed some tests because I've changed the application, right? And it's also error prone, and I definitely don't want to do that, right? That there has to be a better way, and there definitely is, right? So what we can do is we can decouple the configuration of the application with the source code of the application, right? And this is something that most software engineers do, right? We can have something like environment variables, right? Or env files, right? Environment files. And this is something that many runtimes support, for example, like Java, Node.js, and other runtimes support. So this is the problem that we are trying to solve, right? We are trying to externalize the configuration from the application. Now, how does Kubernetes help us in this department? Well, Kubernetes offers us two brand new resources, and that is a secret and configuration map, right? And so these are two resources designed for storing configuration. And so what is a configuration? Well, a configuration is simply a key value pair, right? So we have some key that equals some value. And so in the source code, we refer to the key, right? And at runtime, this key is resolved to the value. So this is quite simple, right? So we have two resources in Kubernetes. One is called secret, one is configuration map. Why do we have two resources? Well, the configuration map is used for key value pairs that are non-sensitive, right? So these are configurations that are, for example, something like configuring a core DNS uses within Kubernetes. Core DNS uses a configuration map to configure itself, right? And when you want to change the configuration of core DNS, you change the configuration map. You can use secret for some sensitive information such as usernames, passwords, and connection strings to a database, etc., right? And secret files, actually, or secret manifests, are encoded in base 64 format, not encrypted, but encoded. And so once we actually create either a secret or configuration maps, we can use them or we can manipulate them with the kubectl command, just like any other Kubernetes resource. So now that we know what problem secrets and configuration maps solve, and we know some basics about secrets and config maps, let's take a look at how we actually create them in Kubernetes, right? So we can use the kubectl, and kubectl has an imperative command to create both config map and secrets. So let's take a look at the config map resource or the configuration map, right? So we of course use kubectl and we use the create command. So what are we creating? Well, we are creating the configuration map, which is called config map, right? Then we select the name, and then we can specify, for example, -- from literal, right? The key value pairs. So for example, key1 equals value 1, and we can specify multiple literals, right? So this is an imperative way of how you can create a config map. You can also create a config map from a file, which is extremely handy, right? So you can create a config map in the same way, right? Create command. What are you creating? A config map, config map name, and then you specify -- from file, right? And path to the file that you want to create. So this is very useful for something like a configuration of certain process, like core DNS, HTTPD, Nginx, etc., etc., right? So these are configuration maps. Of course, we can create a secret. So we have kubectl create, that's the same, right? What are we creating? We are creating a secret. And then one thing that differs is that secret has multiple types, right? So secret can be, for example, a TLS secret or auth secret for authenticating to a Docker registry, right? Or we can have the generic secret, which is probably what you're going to use the most in the beginning. So the generic secret is simply a secret that stores key value pairs, right? And then it's the same, right? So just remember that secrets have multiple types, and take a look at the Kubernetes documentation for more details about the secret types. And then we have our secret name, and the rest is the same, right? We execute -- from literal and specify the key 1, value 1. So username equals something, password equals something, right? And so, as is usual with almost all, with all Kubernetes commands, right? You can execute the -- help to get more information. So kubectl create something, right? So even with create deployment or create config map, -- help, you get more information about how to create the resource, right? Just like with config maps, you can create a secret from file. So that is identical as well. One thing that is definitely very handy is taking a look at the manifest resource of the config maps and secret, right? So we have our config map, and this is a YAML format, the manifest file of the config map. The name of the config map is myconf, right? And then we have some data, right, in the manifest, and then we have our key 1 is equal to value 1, and we have our key 2 is equal to value 2. So in essence, right, within your application, you can reference key 1 and key 2, right? Key 2, which will get resolved at runtime into value 1 and value 2, right? So this is how we reference config maps. So one thing that I definitely wanted to bring your attention to is, as I said, secrets are base 64 encoded, right? Not encrypted. encoded, which means that the data inside of the manifest are also encoded. So despite the fact that the keys, right, the keys are not encoded, the values of the keys are encoded. So they are not human readable by default, which is perfectly fine. At runtime, Kubernetes will decode the values for us, right? So at runtime, our application will be able to say, will be able to refer to something like username and get the actual value, right? But from within the YAML file, you cannot see the actual value just by looking at the value. Remember, base64 is not encryption, so this, for example, does not belong on a publicly available GitHub repository, right? This value can still be easily translated via a simple command, right? So just keep that in mind. This value is not safe, right? The fact that you cannot read this YAML file does not mean that nobody can. It's very simple to translate this value into something that is human readable if somebody wants to. So keep this file somewhere hidden, right? In a hidden repository or within your Kubernetes cluster. So how do we manipulate config maps? Well, just like with any other resource, right? We have kubectl get, just like any other resource, kubectl delete, just like any other resource, and kubectl edit if you want to change the resource, if you want to change a config map or a secret, of course you can, right? With secrets, it's the same. However, if you want to edit the secret, right, you have to provide the values in the base64 encoded values. So how do you get the base64 encoded values? Well, for example, on Linux, right, this is how you get base64 encoded values. And this is why it's very easy to also decode the base64 values, right? Because the same utility that can encode base64 values can decode them as well. So at this point, we know how to create config maps and secrets in Kubernetes. So how do we use them? So if you have a config map or a secret, we can inject them into our application pod, either as an environment variable or mount them as a volume, right? So both of these you can actually do with kubectl. And kubectl uses the set command, right? So you can set the environment on a certain resource. So for example, on a deployment with a certain name, and then you specify from which resource, right? So either from a configuration map or from a secret, right? So this is the same. For a secret, right? kubectl set some environment. So this is inject all of the data as environment variables into all pods that are managed by the deployment named certain name, right? From a certain secret. Or we can mount, right? We can mount the values into a volume, right? And that we can do by using the set command, again, kubectl set, but we are not setting an environment, env, but we are setting volume, right? So we have our volume, and again, what resource are we setting the volume on, right? We are setting it on a deployment, and then we simply add a few options, right? So we are adding the volume, right? Then we are specifying the resource from which we are adding it, right? So either a config map or a secret. Then we are adding the path inside of our application pod. We name the volume, right? And then we provide the configuration map name or a secret name. This was a lot of information, right, over the past couple of videos about config maps and secrets. How do we square that? Like, when do we use each of these resources? Well, there are very few, very easy rule of thumbs, right? Number one, config maps, right? Config maps store data in plain text, and therefore config maps use or store non-sensitive data, right? Secrets generally store data that is more sensitive, like usernames and passwords, ideally for something like staging purposes, dev purposes, etc. Right? What about the environment variables versus mounting the data as a volume? Right? Well, typically, right, we would prefer mounting or injecting the data as an environment variable. So generally, we would try to go for that. However, if we have a lot of data that we want to inject, right, then it might be more useful to actually mount the data as a file, right? Another reason to mount something as a file is that it is actually a file, right? So for example, you can store a TLS secret, right? Or TLS certificate rather into a secret. And then you can mount the TLS certificate in an application as a file and simply use it, right? So this would be a different reason of mounting a file. You can also, for example, if your application uses something like configuration properties, right? You could create a secret from it or create a config map from it and mount it. If you don't want to rewrite your application, then that's also fine, right? So this was just an introduction into configuration maps and secrets. Let's take a look at how they actually work in our Kubernetes cluster in the next guided exercise. So before we get to our guided exercise, what I wanted to do is just explore the concept of environment variables just a little bit. If you are familiar with environment variables, feel free to skip to our guided exercise. If not, then this video might be helpful. So environment variables are just key value pairs that I can set for a specific environment, right? So in my terminal application, I can set a key to be equal to a certain value, right? Once my key is set, what I can do is I can use other commands that refer to the key, and by referring to the key, I can actually get the value that is associated with the key, right? So for example, we can use the echo command. And by referring to the key, right, we actually printed the value. So, so this is, of course, depending on the environment, right? So this syntax, echo and these braces, etc. This is specific to my Linux environment. For example, if we are using PowerShell, right, the syntax is going to be a little bit different. So, for example, in PowerShell, we could do something like env. env colon key equals value, and then we can refer to the value by taking the key, right? So the syntax is different, but the concept is the same, right? The actual syntax is different in PowerShell and, for example, something like Bash. However, we simply refer to the key, right? We refer to the key and we get printed the value. So why is this useful, right? Well, what if the value changes, right? So instead of the key referring to value, we can change the value to be equal to, for example, new value, right? Well, our echo command or our command that refers to the key does not have to change, right? So our command still refers to the same key, right? But our value that the key refers has changed. And so despite our command not changing, the actual output of the command has changed, right? And so this is incredibly useful for us. For example, what if this is something like a username, something like a password, something like a database string connection, right? Something like a configuration setting for your application, background color for something, right? What if this is something like a tweaking of some kind of detail, right, within your application? This gets incredibly powerful for software engineers, and this is a technique that is incredibly useful and helpful in developing software. So this is what we are going to be exploring in our guided exercise. So welcome to our next guided exercise, and in this guided exercise we are going to deploy an application and take a look at how we can actually inject some environment variables and mount a file by using configuration map as well as a secret, right? So within this guided exercise, we are going to deploy a simple application. And actually, let us take a look, right? So within my terminal application, I am in the do100x-apps repository. And in this repository, there is the app-config directory. And in this app-config directory, let's just very briefly explore our application. And so we have our app.js file. And so the main thing that we have to know, right, is that this is an Express.js application, very, very simple application. The main thing that we do is, number one, we print the value of the value of the app_msg environment variable. Right? So this is the syntax for getting the environment variable in Node.js, right? So if the environment variable is not set, this is going to be undefined, right? And once we set it, this is going to be whatever the value is of the app_msg, right? And so we are going to always return this response, right? Right, we are always going to return this response. And at the same time, we are going to try to read within this application. We are trying to read this file, this /op/app_root/secure/myapp.sec, right? This is a file that we are trying to read. And if the file is not within our application or within our container, right? If it is not mounted, then we actually append the error that we get to the response, right? And if it is there, then we actually append the data that we read from the file, right? So this is our very, very simple application. And what we actually also have is the myapp.sec file, right? Which we are going to be mounting. And this is just a security file that contains some username, password, and salt, right? So these are some data that we are mounting in a secret, right? So let's take a look. Let me change into the directory, and we have our Kubernetes directory handy, right? So let me change there as well. And within our Kubernetes directory, we have our deployment. So let's take a look. Our deployment contains is named app config, contains a single container on port 8080 that uses our image. So let us create our deployment. And there we go. So what we have to do, because we are going to be interacting with our application, right? We are going to be sending requests and reading the response. So we will have to create an ingress. And because we are going to be creating an ingress, we have to have a service. So let's actually expose the deployment, right? So kubectl expose. We are exposing the deployment. What is the deployment name? Well, it is the app config, right? And then what was the port? The port was 8080, right? The name can stay the same. We can have the name of the service be app config, and the port of the service can also be 8080. So that's perfectly fine. So we have our service exposed. Let's take a look at our deployment. And our deployment is ready, up to date, available. So that is all good, right? So let me clean this up a little bit. And let's take a look at our ingress. So we have our ingress.yml. And let's just, as usual, let's just double check, right? So we have to change the host. So that's perfectly fine. Outside of that, the service name is app config, and the port number is 8080. So that's exactly what I created. The rest should be fine. So let's change the host. To our host, right? And let us save and exit. And at this point, let me create the ingress. And we have our ingress. So let us actually try to communicate with our application. And there we go. So we got an actual response from our application, right? Our application is up and ready in our Kubernetes cluster. The value of app_msg is undefined. And we got an error because this file is not mounted, right? So finally, we can start getting to creating config maps and secrets. So first things first, let's actually take care of the first error, right? So from our lecture, we know how we create a configuration map. So we can use the kubectl create command. And so we are creating a config map resource. The name for our config map can be app conf map. That's perfectly fine. And then what we are what we are providing is simply the key value pair, right? So the key is going to be app_msg, and the value is going to be, for example, test message, right? So let's create this config map, right? So we have our config map. Let's verify that the config map exists. And we have our app_conf map, right? You can actually get the data from the config map. For example, you can specify the -o command, the output, and YAML or JSON or whatever you want it to be, right? And I forgot to specify the name of the config map. So app_conf map, right? And we have our data is app message or app_msg, and the value is test message, right? So now if I curl my application, what is going to happen? Well, we are going to see the exact same response. And the reason for that is that we have our configuration map, but we have not injected the environment variables into the application pod, right? So now that we have the configuration map, we have to inject the data into our pod. So how do we actually set the environment variables? Well, we can use our kubectl command, right? And we are using the set command. What are we setting? We are setting the environment variables in the deployment, right? Now the deployment name is app_config, and we are setting the environment name from the config map that is named app_conf map, right? And so one thing that you cannot forget is that the config map has to have a slash here. So config map / app_conf map. And so at this point, let's take a look at our pods. Right, so we actually get a new pod because we have updated our deployment. We have updated our deployment has changed, therefore we get a new application pod. And let's actually execute our curl command once again, right? So curl hello.example.com, and we see that the app_msg actually returns some value, right? So that environment variable is now set, right? However, we still don't have the file mounted within the directory, right? So let's fix that right now. Let me change, I'm in the Kubernetes directory, right? So let me change into the app_config directory. And within the app_config directory, I can change into the app directory. And here I have the myapp.sec, right? This is the file that we need. And let me clean this up a little bit. And the way we create a secret is, again, we can use the kubectl command, right? And we can create a secret from file, right? So we execute kubectl create, right? Create command. What are we creating? We are creating a secret. Remember that secret has multiple types, right? We can have a TLS secret. We can have an auth secret. Well, we are creating a generic secret, right? We can provide some kind of a name. This is the suggested name from our guided exercise. So let's go with that, right? And then we have to specify the file name, right? And then the file name is for me, I'm in the app directory. And so the file name is the myapp.sec, right? And so let me verify that. The file name is myapp.sec, so that should be good to go, right? And so there we go. We have our secret app_conf file sec, right? So let's verify the contents of this secret. So kubectl get secret. Then let's take the name of the secret and then JSON, for example, JSON output. And there we go, right? We have our data in the base 64 encoded format, right? We finally have our secret. So what happens when I curl my application? Let's try it. Well, just like before, right? We have our secret, but we did not connect the secret to our application in any way, right? We did not mount it as a file, nor did we inject anything as an environment variable, right? And so in our case, we want to mount it as a file. The fact that we have a secret, well, Kubernetes does not know what we want to do with our secret, right? So we have two pieces of the puzzle and we need to connect them in some way, right? We actually have a handy patch file, right? And so let me change back into the Kubernetes directory. So I'm in the Kubernetes directory. And let me open up the secret.yml file. And essentially, this is a new way of patching a deployment or changing a deployment. What we want to do is essentially within our deployment, we want to edit a deployment such that we want to add these lines, right? So we want to add a new volume. The name of the volume can be whatever we name it, right? That's not that relevant. But the volume is actually based on a secret, and the secret name is our secret that we just created, right? This is the appconf file sec, right? So if you actually named your secret differently, you would have to change it here, right? And so once we actually create a volume, right, then in our container, we actually can create a volume mount, right? And we can mount it to a specified path, right? To a specified path, and the name matches the volume name, right? And it is read-only true. That's perfectly fine, right? So instead of us typing it, we actually have a fully typed part of the YAML file, right? So how do we use this partial YAML file? Well, we can use the patch command, right? The patch command, which essentially says, take the patch file, right? Take this patch file, and the patch file for me is actually just the secret.yml. Take this patch file and change whatever is in the patch file, rewrite whatever is in the patch file, right, for the specified deployment, right? So once again, we are using kubectl, that's perfectly fine. Using the patch command, we are patching the deployment with the name of appconfig, right? And we are saying overwrite the deployment with the specified patch file, right? So whatever is not in the patch file will stay the same, and whatever is in the patch file will get overwritten, right? So we have patched our deployment, right? And let's actually just take a look at our deployment. So I can actually execute kubectl, edit deployment, right, and appconfig. And if I just execute edit without actually trying to edit the deployment, all I want to do is take a look at the mount, right? And that's exactly what we did, right? We added this volume mount, and And we also added this volume, right? So that's exactly what we did with the patch, and everything else from the deployment stayed the same because the patch file did not touch anything else, right? So I have exited without making any changes to my kubectl edit, right? So I have canceled my edit without any changes. And let's take a look at my application. And again, we get a new pod, right? Because we have changed the deployment, we get a new pod. And now when I actually execute my curl command, right? So let me clean this up and execute our curl command. We actually get the app underscore MSG, right? That is still there. And the secret now is mounted, and the contents of the file is the contents of the file that we have created, right? Which is decoded from the base64 value, and that is the readable contents for the application, right? So this was the way that we can actually inject our application with some values that can change from, for example, environment to environment, right? Our application does not have to change. Our application simply refers to some kind of a path, right? Some kind of a file or some kind of a key, right? Environment variable key. And these values can actually change depending on the environment, depending on, for example, whether it's the staging, the dev environment, right, or the production environment. So incredibly powerful stuff and technique. So the only thing that we have left to do is delete the resources that we have created as usual. So let's do that, right? So what we can execute is kubectl delete all as well as the ingress, right? And we can do that because we are in our username -dev namespace, right? And once that is done, we can delete our config map and secret, right? So we have our appconf map and appconf final sec. So let's delete these two. And there we go. So this concludes our guided exercise, and I hope I'll see you in the next video. So welcome to our next lecture, and in this lecture we are going to be talking about the strategies for updating of our applications. So once we have deployed our applications, our workloads to our Kubernetes cluster, updating them becomes a huge part of management of our applications. And Kubernetes offers us a number of ways of simplifying this process, right? So within Kubernetes, there are actually two main ways of how we can implement strategies for updating our applications. The first way is actually using our manager, right? So if we have managed pods, we can use, for example, the deployment, right? If we are using the deployment as the manager of our pods, the deployment itself offers us a number of strategies to help us with deployment of our pods. And then we can actually use the Kubernetes router or some routing strategies to manage rollout of our applications, right? So let's take a look at the deployment strategies first, and then we'll take a look at some advanced routing strategies later. So within our deployment, right, within our manager our pods, there are two main strategies that we can use. And we have the rolling strategy and the recreate strategy, right? And so essentially, let's take a look at how that would go within our Kubernetes cluster. So we have a very simple image, right? Let's imagine that we have a deployment over here, which manages an application which has 3 replicas, right? And right now, the state is over here. So this is our application, our 3 replica application, which uses the version 1, right? The version 1 of our application. And what we want to do, essentially what we want to do is have 0 pods here and all of the pods here, right? So what we want to do is move all of the pods from version 1 to version 2, right? So let's clean that up for a little bit. And so again, all of these pods are managed by our deployment, right? So we have 2 deployment strategies. We have our rolling strategy and our recreate strategy. So let's take a look at our rolling strategy first. When we have our rolling strategy, what happens is that, for example, let's assume that we have updated our deployment, right? For example, we have issued kubectl edit of our deployment, right, and changed the image of our container from the version 1 to version 2, right? And so what happens is that Kubernetes is aware of this change and tries to reconcile this change. So if we have the rolling strategy, essentially we take a look at pod number 1, and pod number 1 gets rolled to version 2, right? So at this point, despite the deployment having 3 replicas, right, being set to 3 replicas, there is a surge of one additional pod, right? This pod number 1 in the version 2, right, is spawning, is getting created in our Kubernetes cluster. And then once it's created, depending on the configuration of our deployment, maybe we have some probes, right? Kubernetes determines whether the pod is ready to serve or not, right? And if the pod is ready to receive requests, right? Once the pod is ready to receive requests, then the original pod, right? Original pod from the version 1 gets scaled down, right? And we destroy it. So at this point, we have 2 pods of version 1 and 1 pod of version 2. And so then Kubernetes takes a look at a second pod of the version 1 and does the same, right? Scales a new pod or creates a new pod from version 2, right? And this new pod, again, is getting created. Again, checks are being run, whether the new pod is ready to receive requests. If the new pod is ready to receive requests, then the original pod is scaled down, right? And in that case, there is only 1 pod remaining from our version 1, and there are now 2 pods from our version 2 deployment. And finally, we only have the last pod from version 1, right? And so again, the same thing happens, right? Pod number 3 spawns. So again, at this point, we have 4 pods, right? We have 1, 2, 3, and 4 pods, right? In this at this time. Then checks are run. If pod number 3 is ready to receive requests, for example, all of the probes pass, right? Then the pod is marked as ready to receive requests, and the original pod gets destroyed, right? And at this point, the version 1 of the application is actually scaled down to 0, right? The whole replica set of the deployment is scaled down to 0, right? And we have our version 2, which is scaled up to 3 pods. So this is our rolling release of our deployment. So let's jump at the beginning of our image, right? And what we have just seen was the rolling strategy, right? Rolling release strategy employed by our deployment. What happens when we employ the recreate strategy for the deployment? Well, when we have our recreate strategy, right? What happens is that essentially we modify the deployment, right? Let's say that we switch from version 1 to version 2, right? And at this moment, the deployment immediately kills or destroys all of the replicas, right? All at once, and starts spawning all of the new replicas, right? In the Kubernetes cluster. So what happens is that there is some time within the Kubernetes cluster where all of the original pods, all of the pods with the version 1 are at 0, right? Are not ready to receive requests because they are in the terminating state. And none of the version 2 replicas are ready to receive requests, right? So with the recreate, there is a time when the deployment is not ready to serve any requests. So these are our two main strategies, right? When do we use each of these? Well, the rolling strategy is the default strategy, right? Why is that? Well, number one, when an issue happens, we still have our original pods, right? When an issue happens with the version 2 pods, version 1 pods do not get destroyed, because remember that the version 1 pods do not terminate until version 2 pods are ready to serve requests, right? There is also zero downtime, right, during an update. So because we progressively spawn new application pods, there is simply no downtime because there is always some pod that is ready to receive requests, right? However, the application must support running an older version and a newer version at the same time, right? So the application must be able to support 2 versions at the same time, and this can get difficult when, for example, the application shares some kind of a persistent volume, or the application has some kind of a stateful logic that would prevent it from having multiple versions at the same time, right? Whereas the recreate strategy, right, simply destroys all of the pods and recreates them, right? And so this is useful when the application does not support running multiple different versions at the same time, right? Or there is some kind of a persistent volume that does not allow multiple pods from accessing it, right? Or simply when we just want to have a new version of our application as soon as possible, and we don't care about the downtime, right? So how do we set our strategy? Well, we are talking about the deployment strategy, right? So this is within our manager object for our pods. and we have the strategy field. So remember that this is right after our spec, right? We are in the first spec, but we are above the template file, right? Or above the template property, excuse me. And we have the strategy where we have our type, right? Type is rolling update, and we can actually configure, if we choose the rolling update, we can actually configure or tweak the property, where we can tweak the search and unavailable properties, right? Where the search essentially says how many more pods can we spawn than we want replicas, right? So if we have, for example, 4 replicas, right? 4 replicas, and max search is 50%, then we can spawn 2 new replicas, right? Or 2 new pods, I mean. And max unavailable is how many pods we can destroy, right? Right away. How many of the old versions of pods we can destroy. So depending on your use case, you can actually tweak the parameters of the strategy. And of course, you can describe. You can use the describe command, right, on some kind of a deployment. So for example, deployment with the name hello, and you can take a look at the strategy type, right? So you can see what is the strategy type, and you can see the parameters of that strategy. A different way of how we can deploy a new version of our application is actually by using a routing strategy, right? So at this point, we have the application already deployed in our cluster, right? In our Kubernetes environment. And what we care is how the users actually see our application, right? And so what we are going to be talking about is two very simple but very effective strategies, right? Which is the blue-green deployment strategy and A/B deployment strategy, right? So let's take a look. So in the blue-green deployment strategy, let's imagine that we have 2 identical deployments, right? We have our blue deployment over here, and we have our green deployment, right? And these are identical at some point, right? And so at this point, we have our blue deployment, which is served by our blue service, and we have our ingress router. And so if a customer, right, or somebody, our user of our application, wants to actually request our application, they make a request to the ingress router, for example, for example.com, right? And the ingress router gets rerouted to the blue service, which serves the request and gets a response from our blue deployment, right? So this is the beginning state. Now, what happens when we want to evolve and change our application, right? Our application is already in our cluster. Well, we have a second environment, right? We have a second deployment in the beginning identical to our blue state. And we call that a green deployment. And so I, as a developer, change my green deployment, change my green application. So I take the feature request and deploy it to my green deployment, right? And we do all of the development there. We do all of our testing there. And the advantage is that we are in our Kubernetes cluster. We are in the environment that we are using, actually, that we will use in production environment, right? We thoroughly test everything that needs to be tested, right? And once we are confident with our changes, the way we deploy this application, right? And let me make this a bit cleaner. The way we deploy this application, right, is simply the only thing that changes is this link, right? So this link gets destroyed and we switch the link from the ingress router to the green service, right? And so suddenly when a customer makes a request or a user of our application makes a request, the request gets rerouted to the green service, which is served by our green deployment, which means that the user will get the new feature, right? So at this point, what will happen? Well, the blue deployment has to be brought up to speed with our previous features, right? So whatever we did to the green deployment has to be done to the blue deployment as well, right? So this is quite an easy thing to do within a Kubernetes cluster, of course. And so we can do that. And once this is done, right, our blue deployment and green deployment are again identical, right? And so what happens when we have a new feature that needs to be implemented? Well, we can implement it in the blue deployment environment, right? So again, I, as the developer, sit down, implement the feature in the blue deployment, right? And we test it in the blue deployment. We do whatever needs to be done to make sure that the feature works, right? And when we are confident that the feature is ready and the customers should see the feature, right? The way we roll out the feature, again, is by changing one link, right? So instead of the ingress router going to the green service, we change the link to the blue service. So the domain, the host, stays the same, example.com, and suddenly whenever our customers, our users of our application create a request, they get served once again by the blue service, which reroutes them to the blue deployment, which means that they get the new functionality once again, right? So this is our blue-green deployment. Very, very simplified, of course. The way you can implement it is in multiple ways, right? This is just a very simple, possibly even naive implementation, but in principle, this is how you could do it, right? You simply have some kind of a router and you simply change the router such that it reroutes the requests to a different environment. Then we have our A/B routing, right? Or A/B strategy, where essentially we have our router and I as a customer, right? Again, want to get, for example, example.com, right? And so I sent a request to the ingress router. And let's say that the ingress router routes my request to a service. And the service has a number of, or routes to a number of pods, right? And the strategy here is that the pods that the service leads to or routes to, right, are, for example, managed by two deployments, right? And one of the deployments uses version 1. One of the deployments uses version 2, right? So a set of customers will get version 1 of the application, while a small set of customers will get a version 2, right? So this is a very, again, very naive implementation of A/B strategy, where essentially what this means is that most customers will get responses from the version 1 of our application, And some customers will get the response from version 2, right? So why is that helpful? Well, we can monitor the logs from version 2. We can monitor the engagement from our users, right? We can monitor a number of statistics that we want to monitor, right? And when we are confident that version 2 of the application works as we would like it to do, right? What we can do is actually scale up this deployment, which is very easy, right? Which will increase the amount of people, the percentage of people that will get responses from version 2, right? And with the same stroke, we can decrease, right? We can decrease the original version 1 deployment, right? Scale down the version 1 deployment. So these are some of the advanced strategies by using routing, right? And these are just some very simple implementations, right, of these strategies. Of course, there are multiple implementations, and especially if you are using something like service mesh on Kubernetes, then you can employ some advanced techniques, like, for example, routing to version B, right? Not based on percentage, but, for example, based on something like a cookie or something like a HTTP header, right? Then you can actually do some very interesting things with your routing. But even in basic Kubernetes without any service mesh, you can employ a number of advanced deployment routing strategies, right? By simply using basic Kubernetes objects. So let's take a look at some of the deployment strategies in our Kubernetes cluster. So welcome to our next guided exercise, and in this guided exercise we are going to explore the deployment strategies for the deployment resource in our Kubernetes cluster. Let me open up my terminal application, and essentially what we are going to do is we are going to create a deployment within our Kubernetes cluster and see how it behaves when we update it. So of course, in my Kubernetes cluster, I am in my username-dev namespace, and there are no resources in my namespace. And so that's pretty good. We can actually create our deployment. So the way we create our deployment is familiar by now. We are using the kubectl command, creating a deployment resource with a particular name, with 5 replicas, right? And we are using the provided image within the guided exercise. And so one thing that we can do right away is we can describe the deployment, right? And what I want to do, what I want to take a look at from the output of the describe command is actually at the strategy type, right? And this is the update strategy type. We did not specify any update strategy type. And so we know that the default strategy type is the rolling update. And the default parameters for our rolling update are 25% unavailable pods and 25% max surge. So what does this mean? Well, when we update our application, what you can think of in terms of the surge, for example, is that the total pods, right? So we have some kind of replica setting. We have 5 desired replicas. Well, we have 25% surge pods. This means that upon updating of our deployment, the total amount of pods or total number of pods should not exceed 125 percent of the replicas, right? The configured replicas, and the unavailable, maximum unavailable pods is essentially the number of pods that we can destroy at any given time out of the set replicas, right? So this is all well and good. Let's take a look at our pods. And indeed, we have 5 pods in the running state, right? So what I can do is I can clear this and execute my kubectl get pods one more time, but with the -w flag, right? Which means that essentially it instructs the kubectl to wait for changes, right? And in a different terminal, I can edit my deployment. And so what we want to do is we want to edit the image, right? So we are editing the image for the container, and we are simply incrementing the tag of the image from version 1-external to version 2-external, right? So there we go. That's all that we did, right? So now the image is version 2-external. And what I can do is save and exit my YAML file, right? And switch to my previous terminal. And there we see a lot of output. And so let's wait for the output to stop and analyze the output. So let's analyze our output of the kubectl get pods. So we know that the max search is 125% of our 5 pods, right? Which is 6 pods in total. So we begin with 5 pods in the running state, right? These are our original 5 pods. And then I issued the change of the deployment. So what happens is that we immediately start terminating 1 pod, right? So with our 5 pods, we have only 4 pods at this state. So what that means is that Kubernetes can spawn more pods, right? We have a budget. So Kubernetes does spawn multiple pods. And then let's take a look at our running pods. So we have, at this point, we have only 4 pods in the running state, right? Then our terminating pod actually finishes terminating, right? So we have 0 out of 1. Then we have 2 pods that start in the running state. So this means we have 6 pods, right? And at this point, we have a new pod that starts terminating. So we have 5 pods, right? We have 1 pod that starts running. So we have 6 pods. We finish termination. We finish termination. We start a new termination. So we have 5 pods, right? We start a new termination. So we have 4 pods. And we start a new container. So we have 5 pods. We start new termination. So we have 4 pods, and we finally finish our deployment. So we have 5 total pods, right? At any given point, our deployment did not exceed 6 pods in the running state, right? We could have had more containers in the pending state. That's perfectly acceptable and fine, but not in the running state, right? And so now if I execute Control-C to exit my kubectl get pods -w and execute, let's clear this up actually, and execute simple kubectl get pods, I will only have 5 pods, all in the running state. And so let's actually verify the logs of our application. And we see that we have our Node.js application running on version 2.0. So our application was indeed updated. So that is all for our guided exercise. The only thing that is left is actually clean up our deployment. So let's do that with a simple delete command. And I hope I'll see you in the next video. So in this video, I would like to recognize the distance that we have made together. In this course, we have covered a lot of ground and a lot of concepts about Kubernetes. We have started out by talking about what it means for an application to be managed by Kubernetes and what are some of the advantages for an application to be managed, right? Why do we want for Kubernetes to manage an application? We talked about networking and how do we expose an application within a Kubernetes cluster, and how do we actually route external requests to our application, right? We talked about various concepts such as liveness probes and readiness probes, right? Proving that our application is ready to receive requests, and what do we do when it is not? We decoupled our application from the configuration of the application. And we also took a look at how do we roll out new versions of our application in the Kubernetes cluster, right? What are some of the strategies that we can employ in our Kubernetes cluster? So this is a lot of information, and I would definitely like to recognize and congratulate you on getting this far. If you are interested in gaining more knowledge about Kubernetes, take a look at our third course in this specialization, where effectively what we try to do is gain deeper knowledge about Kubernetes through the lens of Red Hat OpenShift, which is another distribution of Kubernetes. So I hope that this course has been useful for you, and I hope that I'll see you in our third and final course of our specialization.